Long before familiar animals filled forests, oceans, and skies, life was already experimenting. Bodies grew where no bodies had grown before. Eyes appeared in unexpected places. Limbs multiplied, vanished, or turned into something else entirely. Some creatures became enormous. Others became almost invisible. Many vanished forever, leaving only traces in stone. Others survived, quietly strange, still moving through the modern world as reminders that normal was never the plan. This is a journey through those animals, not myths, not monsters, but real living beings shaped by deep time, chance, and survival. Some walked the earth hundreds of millions of years ago. Some are still alive right now, hiding in oceans, forests, and burrows. All of them stretch the idea of what an animal can be. Welcome to the Sleepy Scientist. If this kind of calm exploration into the animal world helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. For a long time, Hallucigenia looked less like an animal and more like a mistake. It was small, soft-bodied, and lived more than 500 million years ago during the Cambrian period, a time when animal life was rapidly experimenting with form. When its fossils were first uncovered, Hallucigenia appeared so unfamiliar that scientists genuinely struggled to understand how it was supposed to exist at all. At first glance, the creature seemed to be walking on rigid spikes, with soft tentacle-like structures waving uselessly in the air. Its body looked fragile, almost inside out. There was no obvious head, no clear tail, no clear front or back. Even deciding which side was up proved surprisingly difficult. The name Hallucigenia reflects this confusion. It was named not because it caused hallucinations, but because it looked like something imagined rather than evolved. Early reconstructions based on limited fossil material showed an animal that appeared anatomically implausible. An organism balanced awkwardly on sharp spines would not last long in any environment, Cambrian or otherwise. The key problem was perspective. Hallucigenia fossils are usually preserved as flattened impressions in rock, with only part of the animal visible. Important features overlapped or were missing entirely. For decades, scientists were essentially trying to reconstruct a three-dimensional animal from a two-dimensional shadow. As more fossils were discovered, especially from sites like the Burgess Shale in Canada and later deposits in China, the picture slowly began to change. Researchers noticed that the supposed walking spikes were actually defensive spines on the animal's back. The softer structures, once thought to be useless appendages waving into the water, were instead the legs. Hallucigenia had been upside down. Once flipped the right way up, the animal began to make much more sense. It walked on pairs of soft-clawed limbs, similar to those of modern velvet worms. Above those legs rose stiff spines, likely used to discourage predators in a world where predation was becoming increasingly common. What once looked impossible suddenly looked practical. Even the head, long missing from early interpretations, eventually revealed itself. Subtle fossil details showed a small head with simple eyes and a mouth at one end of the body. It was not dramatic or oversized, but it was enough to establish orientation and movement. This slow correction tells an important story, not just about hallucigenia, but about how science works. Early paleontologists did not fail by getting it wrong. They worked with incomplete evidence, revised their ideas as new data appeared, and gradually converged on a better explanation. Hallucigenia did not change. Understanding of hallucigenia did. Modern studies place hallucigenia among the lobopodians, a group of early animals related to the ancestors of arthropods. That means this strange creature sits near the deep roots of insects, spiders, and crustaceans. Its soft legs and segmented body hint at a future where exoskeletons, jointed limbs, and complex movement would dominate animal life. In its own time, hallucigenia was not a monster or an outlier. It was simply one participant in a crowded competitive ecosystem, filled with unfamiliar shapes. The Cambrian seas were home to animals with grasping appendages, armoured plates, and sensory organs arranged in ways rarely seen again. Hallucigenia fit into that strange crowd perfectly. Its oddness today comes from distance. 500 million years of extinction, replacement, and refinement have narrowed the range of body plans that survive. What remains feels normal only because everything else is gone. There's also something quietly humbling about hallucigenia. An animal small enough to fit in the palm of a hand managed to confuse human experts for decades. Not because it was complicated, but because it did not fit modern expectations of how animals should look. Hallucigenia reminds us that evolution does not aim for clarity. It does not label front from back or design bodies to be easily interpreted by future observers. It experiments, keeps what works, and discards the rest. Sometimes what works looks deeply strange. In that sense, hallucigenia was never backwards, broken, or upside down. It was simply an animal living comfortably in a world that no longer exists, waiting patiently for understanding to catch up. Opabinia did not look like it belonged anywhere familiar, even among the strange animals of the Cambrian seas. Living more than 500 million years ago, Opabinia was a soft-bodied animal only a few centimeters long, yet it managed to leave a lasting impression on science that far outweighed its size. When its fossils were first described, they caused genuine disbelief. Some researchers initially thought the reconstruction had to be wrong, not because the fossil was unclear, but because the animal itself seemed too strange to be real. The most immediately striking feature of Opabinia was its eyes. Not 2, not 3. 5 separate eyes sat on top of its head, arranged in a gentle arc. Each eye was likely capable of detecting light and movement, giving Opabinia an unusually wide field of view for its time. In the crowded, predator-filled waters of the Cambrian, awareness mattered. Being able to see danger approaching from multiple directions could mean the difference between survival and becoming a meal. But Opabinia's eyes were only the beginning. Extending from the front of its head was a long, flexible proboscis, ending in a claw-like structure. This was not a nose, and not quite a limb. It functioned as a grasping tool, capable of reaching down into the sediment, picking up small food items, and delivering them to the mouth, which faced backward underneath the head. That unusual arrangement meant Opabinia likely fed while swimming just above the seafloor. The proboscis could probe soft mud for small organisms, while the eyes scanned the water above for danger. Rather than rushing or chasing, Opabinia appears to have lived a careful, methodical life, collecting food piece by piece in a world that rewarded caution. Its body was segmented and flanked by broad overlapping side lobes, which likely helped with swimming. These lobes would have rippled gently, allowing Opabinia to glide through the water with controlled movements rather than bursts of speed. At the rear, a fan-shaped tail provided steering and stability. There was no hard shell, no armor, no spikes. Opabinia relied on awareness, maneuverability, and timing. Its design suggests an animal finely tuned to its environment, not a failed experiment, but a successful solution to a very specific ecological niche. When paleontologist Harry Whittington presented Opabinia to a scientific audience in the 1970s, the reaction was reportedly laughter. Not mockery, but astonishment. The animal challenged assumptions about what early animals should look like. 5 eyes seemed excessive, a clawed proboscis seemed implausible, and yet the fossil evidence was clear. As more specimens were examined, skepticism gave way to acceptance. Opabinia was not a mistake of preservation or imagination. It was real. What makes Opabinia especially important is not just its appearance, but what it reveals about early animal evolution. During the Cambrian period, ecosystems were rapidly diversifying. Predators were emerging. New feeding strategies were being tested. Sensory systems were expanding in complexity. Opabinia shows that there was no single path forward. Modern animals tend to follow recognizable patterns: heads at the front, eyes in pairs, mouths pointing forward. Opabinia ignored those conventions entirely. Its mouth faced backward. Its eyes multiplied. Its feeding tool floated freely in front of its body like a living extension cord. Over time, many of these experimental designs disappeared. 5 eyes did not become standard. Proboscis-based feeding did not dominate marine ecosystems. Natural selection narrowed the field, favoring designs that balanced efficiency, development, and energy cost. But for a time, Opabinia's design worked. It survived in its environment long enough to fossilize, reproduce, and hold its place among a diverse community of early animals. That alone is evidence of success. Evolution does not preserve curiosities out of kindness. It preserves what functions. Opabinia also serves as a reminder that the early history of animal life was not a slow, orderly march toward familiar forms. It was a burst of creativity shaped by physics, chemistry, and chance. Some ideas stuck, others vanished. All were tested. Today, Opabinia feels alien because it represents a branch of possibility that ended. Its body plan left no direct descendants. Its 5 eyes stared out at a world that no longer exists. And yet, without animals like Opabinia exploring what was possible, the path toward modern life would have looked very different. In the end, Opabinia rewrote expectations not by being strange for its own sake, but by revealing just how open-ended early evolution truly was. It shows that what seems normal now is only a small surviving slice of what once lived, swam, and looked back at the world with 5 curious eyes. Anomalocaris did not just hunt in the Cambrian seas, it reshaped them. More than 500 million years ago, when most animals were small, soft, and vulnerable, Anomalocaris stood apart as something entirely new. It was large for its time, powerful, fast, and built with a level of specialization that made it the most formidable predator the early oceans had ever seen. For a long time, scientists did not realize Anomalocaris was a single animal at all. Its fossils were discovered in pieces. One fossil showed strange spiny limbs. Another revealed a circular, tooth-lined structure. A third displayed a broad, segmented body with flaps along its sides. For decades, these parts were classified as belonging to different organisms. Only later did researchers realize they were looking at fragments of the same creature. When assembled correctly, Anomalocaris emerged not as a curiosity, but as a complete and highly effective hunter. At full size, Anomalocaris could reach over 1 meter in length, enormous by Cambrian standards. In a world where many animals measured just a few centimeters, this alone made it imposing. But size was only part of the story. At the front of its body were 2 long jointed appendages, lined with sharp, inward-facing spines. These grasping arms were flexible and precise, capable of reaching forward, seizing prey, and pulling it inward. They were not crude tools. Fossil evidence shows they were articulated, allowing controlled movement rather than simple snapping. Between those arms sat Anomalocaris's mouth, a circular structure made of overlapping plates arranged like a ring of teeth. This mouth did not open and close like a jaw. Instead, it functioned more like a rotating crusher, gripping and processing food from multiple angles at once. Early debates questioned whether this mouth was strong enough to break hard shells. Some scientists suggested Anomalocaris might have fed only on soft-bodied animals. Later studies of wear patterns and biomechanics indicated that while it may have struggled with the hardest shells, it was more than capable of handling a wide range of prey. In other words, Anomalocaris was not picky. Its body was built for motion. Along its sides ran a series of overlapping flaps, which moved in coordinated waves. This arrangement allowed Anomalocaris to swim efficiently, generating lift and thrust while maintaining stability. It could glide through the water rather than dart clumsily, conserving energy while staying mobile. Large, stalked eyes sat atop its head, offering a wide field of vision. These eyes were complex with many individual lenses, making them well suited for detecting movement and contrast. In the dim, particulate-filled waters of the Cambrian seas, being able to see clearly was a major advantage. Taken together, these features made Anomalocaris something unprecedented. It was not just an animal that ate other animals, it was an active, mobile predator with specialized tools for detection, capture, and consumption. This had profound consequences for the ecosystem around it. Before predators like Anomalocaris appeared, many early animals relied on passive defense. Some had hard shells, others burrowed into sediment, many simply drifted or crawled slowly, with little need for speed or awareness. Anomalocaris changed the rules. Its presence introduced sustained predation pressure, forcing other animals to adapt. Shells became thicker, burrowing became deeper. Body plans shifted toward mobility, sensory awareness, and defensive structures. In this way, Anomalocaris did more than hunt. It drove evolution. There is something striking about how modern its role feels. Strip away the unfamiliar anatomy, and Anomalocaris begins to resemble later apex predators in function, if not form. It patrolled its environment, it targeted smaller animals, it exerted top-down control on the ecosystem. Yet its appearance remains deeply alien. There is no living animal quite like Anomalocaris today. Its grasping arms are not quite limbs, its mouth is not quite a jaw, its body flaps are not quite fins. It represents a lineage that explored a different solution to the problem of predation, one that ultimately vanished. That disappearance does not mean failure. Evolution is not a contest where only one design wins forever. It is a shifting landscape where success is temporary and context-dependent. Anomalocaris was superbly adapted to its time and place. When conditions changed, when ecosystems grew more complex, and when new competitors emerged, its particular combination of traits no longer held the same advantage. The world moved on. What remains is the fossil record and the reminder it carries. Anomalocaris shows that the concept of a predator did not gradually emerge from simple beginnings. It arrived early, fully formed, and unapologetically effective. Long before teeth and claws took familiar shapes, nature had already produced something capable of hunting with speed, precision, and intent. In the Cambrian seas, Anomalocaris was not a monster. It was not an anomaly. It was simply an animal doing exactly what evolution allowed it to do. And for a brief moment in deep time, it ruled. Pikaia would have been easy to miss. It was small, soft-bodied and unremarkable at first glance. It did not have claws, armor, spines, or oversized eyes. It did not hunt. It did not dominate. In the crowded Cambrian seas, surrounded by far stranger and more dramatic animals, Pikaia would not have drawn much attention at all. And yet, few animals that ever lived mattered more. Pikaia lived more than 500 million years ago and measured only a few centimeters in length. Its body was slender and flattened, tapering gently at both ends. It swam by undulating from side to side, moving with a quiet, eel-like motion just above the seafloor. What made Pikaia extraordinary was not how it looked, but how it was built. Running along its back was a flexible supporting structure, a stiffened rod that gave the body shape while still allowing movement. This structure, known today as a notochord, provided internal support without rigid armor or an external shell. Alongside it ran simple muscle blocks arranged in repeating segments, allowing controlled, coordinated motion. This arrangement may sound technical, but its significance is hard to overstate. Pikaia represents one of the earliest known chordates, a group defined not by size or lifestyle, but by a particular body plan. That plan includes a notochord, segmented muscles, and a central nerve cord running along the back of the body. Every vertebrate alive today follows this basic layout. Fish, amphibians, reptiles, birds, mammals, humans. The blueprint begins here. At the time Pikaia lived, most animals relied on external structures for support. Shells, plates, spines, and armor were common solutions. Pikaia took a different path. Its support came from within, allowing greater flexibility and more refined movement. It was not fast or powerful, but it was efficient. That efficiency mattered. By having an internal support structure, Pikaia could move in smoother waves, wasting less energy as it swam. Its muscles worked against a central axis rather than pulling against a rigid exterior. This allowed for better control, even at small size. Pikaia also shows early evidence of bilateral symmetry, meaning its left and right sides were mirror images. This symmetry, paired with directional movement, gave it a clear front and back, an important step toward purposeful navigation rather than drifting. There is no evidence that Pikaia was a predator. It likely fed on small particles or microorganisms, gathering food from the water or sediment. It lived a quiet life, avoiding danger rather than confronting it. That quietness is part of the story. Evolution does not always advance through dominance or spectacle. Sometimes it progresses through persistence, through designs that simply work well enough to continue. Picaia's body plan did not make it king of the Cambrian seas, but it allowed it to survive, reproduce, and leave descendants. Those descendants would eventually refine the design. The notochord would become reinforced and segmented, evolving into a backbone. Muscle blocks would become more specialized. Nervous systems would grow more complex. Heads would develop more advanced sensory organs. Limbs would appear, disappear, and reappear in new forms. But the underlying structure would remain. Pikaia shows that the foundations of vertebrate life were laid early, quietly, and without fanfare. While other Cambrian animals explored extreme shapes and experimental designs, Pikaia established a framework that proved remarkably adaptable. This adaptability is why the chordate body plan survived while many others vanished. External armor works well until environments change. Specialized feeding structures succeed until food sources shift. But an internal framework, capable of modification without complete redesign, offers long-term flexibility. Pikaya's significance was not recognized immediately. When it was first described in the early 20th century, it was debated whether it truly belonged among chordates. Its features were subtle, its preservation was imperfect, its importance was easy to underestimate. Later discoveries, including better preserved fossils and comparisons with similar early animals, strengthen the case. Today, Pikaya is widely regarded as one of the clearest early examples of the chordate lineage. There is something gently ironic about this. In a time defined by evolutionary excess, by animals pushing size, armor, and sensory systems to extremes, the creature that mattered most was the one that stayed simple. Pikaya did not rewrite ecosystems, it did not drive arms races or force dramatic adaptations in others. It simply existed in a way that could be built upon. If hallucigenia shows how strange early animals could be, and Anomalocaris shows how powerful they could become, Pikaya shows how quietly transformative they could be. It reminds us that evolutionary importance is not measured by how impressive an animal appears, but by how enduring its solutions turn out to be. Long after the spines, claws, and bizarre appendages of the Cambrian faded into stone, the body plan carried by Pikaya continued onward, reshaped again and again, eventually walking onto land, taking to the air, and looking back at its own origins. All of that traces back to a small, soft-bodied animal swimming gently through ancient seas, changing everything without ever drawing attention to itself. Dunkleosteus did not need teeth to be terrifying. Living around 360 million years ago during the Devonian period, Dunkleosteus was one of the most formidable animals ever to patrol Earth's oceans. It was a fish, but not in the way most people imagine fish. Its head and upper body were encased in thick plates of bone, forming a natural suit of armor that made it look more like a moving fortress than a swimmer. At full size, Dunkleosteus could reach lengths of 8 to 10 meters, placing it among the largest predators of its time. In the Devonian seas, this made it an apex hunter with very little competition. Most other animals were smaller, slower, and far less protected. The most distinctive feature of Dunkleosteus was its mouth. Instead of rows of teeth, its jaws were formed from sharpened bony plates. These plates met at precise angles, creating self-sharpening edges that functioned like enormous blades. As the jaws closed, the edges slid past each other, maintaining a cutting surface without the need for replacement teeth. This design was brutally effective. Biomechanical studies suggest that Dunkleosteus could open its mouth extremely quickly, creating a powerful suction effect that pulled prey inward. Once caught, the jaws snapped shut with tremendous force. Estimates based on skull reconstruction and muscle attachment points indicate bite forces comparable to, or exceeding, those of many modern large predators. The result was an animal capable of slicing through flesh, crushing bone, and dispatching prey in a single motion. Dunkleosteus did not chase fast-moving fish across long distances. Its heavy armor would have made sustained high-speed pursuit inefficient. Instead, it likely relied on short bursts of movement, ambush, and sheer power. Its armored head allowed it to absorb impacts and resist counterattacks, while its jaws did the rest. Fossil evidence shows that Dunkleosteus fed on a wide range of prey. Smaller fish, armored placoderms, and even other Dunkleosteus individuals appear in the fossil record as victims. Bite marks on fossilized bones suggest that cannibalism was not uncommon. In a world where size and strength ruled, even your own species was not necessarily safe. Its armor served multiple purposes. It protected vital organs at the front of the body, where attacks were most likely to land. It also added mass, stabilizing the animal during feeding strikes. The rear of the body, which was not armored, likely provided propulsion through a strong tail, balancing protection with mobility. Dunkleosteus was not clumsy. Despite its bulk, its design suggests a capable swimmer, able to maneuver effectively in open water. The combination of speed over short distances, overwhelming bite force, and defensive armor made it an exceptionally well-rounded predator. In its time, Dunkleosteus sat at the top of the food web. Few animals could challenge it directly. Those that did would have faced a mouth that functioned like a pair of living shears. There's something especially striking about Dunkleosteus because it represents a path evolution later abandoned. Modern fish rely on replaceable teeth, rather than permanent bone blades. Armor fell out of favor as speed, agility, and sensory precision became more important. But during the Devonian, this design worked. Dunkleosteus thrived in warm, shallow seas filled with diverse marine life. The oceans were crowded, competitive, and dangerous. Predators were pushing boundaries, and prey species were experimenting with new defenses. Dunkleosteus answered this arms race with raw force and protection. Its dominance did not last forever. Environmental changes, shifting ecosystems, and mass extinctions eventually reshaped marine life. Placoderms, the group Dunkleosteus belonged to, vanished entirely. Their lineage ended, leaving no direct descendants. What remains are fossils, and the impression of an animal that ruled its world with efficiency rather than subtlety. Dunkleosteus reminds us that evolution does not follow a single trajectory toward refinement or elegance. Sometimes it favors overwhelming strength. Sometimes it builds tools that look more like weapons than body parts. And sometimes those designs succeed brilliantly, even if only for a geological moment. In the ancient seas of the Devonian, Dunkleosteus was not a primitive fish waiting to be replaced. It was a fully realized predator, perfectly suited to its environment, cutting its way through the oceans with jaws made of bone and a body built to dominate. For its time, nothing swam higher. Helicoprion looked like a rumour carved into stone. When its fossils were first discovered, they showed something deeply unsettling, a tight spiral of sharp teeth, arranged like a circular saw blade. There was no obvious jaw attached, no skull, just the whirl. For a long time, no one could agree on where this structure belonged, or how an animal could possibly use it without injuring itself. And yet Helicoprion was very real. It lived roughly 290 million years ago, during the late Paleozoic era, and belonged to an extinct group of cartilaginous fish related to modern sharks and rays. Like them, Helicoprion had a skeleton made mostly of cartilage, which does not fossilize easily. That made the teeth the most common, and often the only, parts preserved. Those teeth told a strange story. The spiral was not decorative. It was not a defensive weapon. It was the animal's lower jaw. Unlike modern sharks, which continuously shed and replace teeth in neat rows, Helicoprion kept every tooth it ever grew. New teeth formed at the back of the mouth and pushed older ones forward, rolling them inward in a growing spiral. Over time, this created a tightly coiled whorl that sat inside the lower jaw, with the cutting edges exposed. For decades, scientists debated where this whorl was positioned. Some early reconstructions placed it protruding from the mouth like a buzzsaw. Others imagined it curled beneath the chin or embedded deep in the throat. These ideas were imaginative but biologically awkward. The breakthrough came much later with advances in imaging technology. High-resolution scans of rare fossils preserved inside rock allowed researchers to see how the whorl fit within the jaw structure. What emerged was far more elegant than earlier guesses. The spiral sat neatly in the lower jaw, with the upper jaw closing down over it. As Helicoprion bit down, prey would be pulled inward by the curvature of the teeth. The motion sliced flesh efficiently, guiding food deeper into the mouth rather than pushing it out. The oldest teeth sat at the center of the spiral, worn but still functional, while newer, sharper teeth did most of the cutting at the outer edge. This design meant Helicoprion did not need to replace teeth. Nothing fell out. Nothing was wasted. The jaw simply grew longer and more tightly coiled over time. It is likely that Helicoprion fed on soft-bodied prey such as squid-like animals and fish, rather than heavily armoured creatures. This slicing action of the whirl would have been devastating against flesh, even if it struggled with hard shells. The shape of the spiral also suggests a feeding style based on precision rather than brute force. Helicoprion was probably not a bone crusher like some later predators. Instead, it was a specialist, using a unique mechanical solution to solve the problem of capturing slippery prey in open water. Its body, though rarely preserved, was likely streamlined and shark-like. The real oddity was not its silhouette, but its mouth. From the outside, Helicoprion may have looked relatively ordinary. Inside, it carried one of the strangest feeding tools ever evolved. What makes Helicoprion especially fascinating is how long it persisted. This was not a short-lived experiment. The genus survived for millions of years, long enough for the spiral jaw to prove itself as a viable design. Evolution does not tolerate novelty for novelty's sake. If a structure persists, it works. And yet, no living animal uses anything quite like it. Modern sharks solve the problem of feeding differently, with rows of replaceable teeth that prioritize flexibility over permanence. Helicoprion took the opposite approach, building a single, ever-growing cutting device that never reset. There is something almost industrial about the design, as if nature briefly decided to test a machine-like solution in flesh and cartilage. The result feels oddly modern, despite its age. Helicoprion also reminds us how incomplete the fossil record can be. For decades, scientists knew the teeth, but not the animal. Interpretation lagged behind discovery. Understanding came not from finding a completely new fossil, but from looking more carefully at what was already there. Once the jaw was placed correctly, Helicoprion stopped being absurd and started being clever. The spiral was not a flaw. It was the point. In the ancient oceans, Helicoprion cut its way through prey with a mouth that grew as it fed, carrying its entire dental history with it. Every bite added another turn to the spiral, another record of survival etched into bone. It was strange, certainly, but it was not confused. Helicoprion knew exactly how to use its saw. Jacalopterus did not feel small in any sense of the word. Living roughly 390 million years ago during the Devonian period, Jacalopterus was a sea scorpion, an arthropod related to modern horseshoe crabs and arachnids, but calling it a scorpion only hints at its true scale. At full size, Jacalopterus may have reached lengths of over 2.5 meters, making it one of the largest arthropods that ever lived. In the ancient waters it inhabited, this was not just large, it was overwhelming. Jacalopterus had a long segmented body covered in a hard external shell, jointed limbs, and large grasping appendages at the front. Its body plan followed the familiar arthropod design, but scaled up far beyond what feels comfortable today. Each segment added mass and leverage. Each joint added reach and control. Its most striking weapons were its front limbs, equipped with spines and hooks that could seize prey with precision. These appendages were not decorative. They were tools built for capture, able to grab, hold, and manipulate struggling animals in murky water. The head region housed large compound eyes, giving Jacalopterus a broad visual field. While these eyes were not capable of the fine detail seen in modern vertebrates, they were excellent at detecting movement. In shallow, light-filled waters, that mattered more than clarity. Anything that moved risked being noticed. Unlike many later marine predators, Jacalopterus did not rely on speed alone. Its size allowed it to dominate through presence. Smaller animals could not easily fend it off. Armor that protected against fish or smaller arthropods offered little resistance against something this large and strong. Its diet likely included fish, smaller arthropods, and other marine animals unlucky enough to cross its path. Fossil evidence suggests that Jacalopterus lived in estuaries and coastal waters, environments rich in life but often shallow and confined. In such spaces, a large ambush predator had a significant advantage. Jacalopterus could lurk near the bottom, partially concealed waiting for movement. When prey came within range, the grasping limbs could snap forward, pulling the animal in before it had time to react. Escape options were limited. Few creatures shared its size or strength. One of the most common questions surrounding Jacalopterus is how an arthropod managed to grow so large at all. Today, insects and their relatives are constrained by their physiology. Their external skeletons must support their weight. Their breathing systems rely on diffusion rather than lungs, limiting how much oxygen can be delivered to tissues. In Jacalopterus's time, conditions were different. The Devonian period experienced higher oxygen levels than those found in many later eras. This increased availability of oxygen made it easier for large-bodied arthropods to supply their tissues with what they needed. In aquatic environments, buoyancy also reduced the strain of supporting a heavy body, allowing size to increase without immediate collapse under its own weight. Jacalopterus took full advantage of these conditions. Its external shell provided protection and structure, while the water helped support its mass. Its size, in turn, reduced the number of predators capable of threatening it. This created a feedback loop where being large made survival easier, which allowed large size to persist. But size always comes with trade-offs. A massive arthropod requires more energy. It needs abundant food. It is less agile than smaller relatives. If environments change, if oxygen levels drop, or if prey becomes scarce, that size can quickly become a liability. Jacalopterus thrived during a time when the balance favored it. Shallow seas, rich ecosystems, and favorable atmospheric conditions aligned to make gigantism viable. For millions of years, this strategy worked. There is also something deeply unsettling about Jacalopterus because it occupies a space that feels wrong to modern intuition. Arthropods today are small, they scuttle, they buzz, they hide. Jacalopterus overturns that expectation entirely. Imagine an animal shaped like a scorpion, but long enough to rival a small car. Imagine that animal moving through water with deliberate force, its limbs unfolding as it reaches for prey. This was not a novelty. It was a functioning predator, perfectly suited to its time. Eventually, the world changed. Oxygen levels fluctuated, ecosystems shifted, new predators emerged, including early sharks and bony fish that brought different advantages to the hunt. The era of giant arthropods slowly came to an end. Jacalopterus did not shrink. It vanished. Its disappearance was not sudden, and it was not unique. Many large arthropods followed the same path, leaving behind only fossils and the reminder that size limits are not fixed. They depend on context. Jacalopterus shows that the modern world is not the only way the world can be. There was a time when arthropods ruled the water, when external skeletons grew enormous, and when scorpion-like hunters sat near the top of the food chain. It also reminds us that what feels impossible today was once routine. Arthropods did not know they were too big. They simply lived. In the Devonian waters, Jacalopterus was not an outlier or a curiosity. It was a dominant presence, a moving shadow in shallow seas, built from segments and spines, thriving in conditions that allowed an arthropod to become a giant. For a while the world was large enough to let it happen. Leedsichthys was enormous, but it was not a terror. Living during the Jurassic period around 160 million years ago, Leedsichthys was the largest bony fish to ever swim through Earth's oceans. Estimates vary, but many scientists believe it reached lengths of over 15 meters, with some reconstruction suggesting even more. By any measure, it dwarfed most other fish of its time, and yet despite its size, Leedsichthys did not hunt large prey. It did not chase, it did not bite, it filtered. Leedsichthys fed on plankton, the tiny drifting organisms that float through sunlit ocean waters. This alone makes it remarkable. Gigantism is often associated with power, speed, and aggression. Leedsichthys followed a different path entirely, growing massive by feeding on some of the smallest forms of life in the sea. Its body was long and streamlined, built for steady movement rather than bursts of speed. The head was wide, with a huge mouth that could open to take in large volumes of water. Inside that mouth were specialized structures called gill rakers, fine comb-like elements that strained plankton from the water as it passed through. As Leedsichthys swam forward, water flowed into its mouth, across the gill rakers, and out through the gill openings. Food was trapped. Water escaped. The process repeated continuously. This feeding method required abundance. Plankton may be tiny, but it can exist in staggering quantities. During the Jurassic, warm seas and high productivity meant plankton blooms could support animals of exceptional size. Leedsichthys tapped into this energy source directly, converting countless microscopic meals into a giant body. Unlike predators that depend on finding and overpowering individual prey, Leedsichthys relied on consistency. As long as it swam through productive waters, food came to it. This allowed the fish to grow larger without needing stronger jaws or sharper teeth. Its skeleton, made of bone rather than cartilage, distinguished it from later giants like sharks and rays. That bony framework provided rigidity and support, helping to manage its size while maintaining efficient swimming. At the same time, much of its skeleton was relatively lightly built, reducing weight where possible. Fossils of Leedsichthys are rare and often fragmentary. Large bones, gill structures, and fin elements have been found, but complete skeletons are elusive. This has led to debate over its exact size and shape. Even so, the available evidence consistently points to an animal far larger than any modern bony fish. What makes Leedsichthys especially interesting is its place in marine ecosystems. It shared the oceans with large predatory reptiles, including pliosaurs and ichthyosaurs. Despite its size, Leedsichthys was not armoured or heavily defended. Its survival strategy did not involve fighting back. Instead, its sheer scale may have offered some protection. While juveniles would have been vulnerable, fully grown individuals were likely too large for most predators to handle. Attacking such a massive, fast-moving filter feeder would have been risky and energetically expensive. Leedsichthys shows that becoming large does not require becoming dangerous. This strategy appears again later in Earth's history. Modern baleen whales follow a similar path, filtering plankton and small fish rather than hunting large prey. Leedsichthys reached this solution long before whales existed, demonstrating that evolution often revisits successful ideas. Eventually, Leedsichthys disappeared. The reasons are not entirely clear, but changes in ocean conditions, plankton availability, and marine ecosystems likely played a role. When the food web shifts, specialists are often the first to feel the pressure. Its extinction does not diminish its success. For millions of years, Leedsichthys thrived as a gentle giant of the Jurassic seas, moving steadily through warm waters, feeding on clouds of microscopic life. There is something quietly striking about an animal of such size surviving on such small food. It challenges the assumption that power must be violent or that dominance requires aggression. Leedsichthys ruled its niche by efficiency, not force. In a sea filled with teeth, claws and speed, Leedsichthys chose patience and abundance. And for a long time, that was more than enough. Spinosaurus has spent more than a century refusing to stay still, not in life and not in science. First described in 1912 from fossils found in North Africa, Spinosaurus immediately stood out. Even from fragmentary remains, it was clear this dinosaur did not match the familiar image of a large land predator. Its bones hinted at something elongated, something unusual, something that did not sit comfortably alongside animals like Tyrannosaurus. Then, for a long time, Spinosaurus vanished. The original fossils were destroyed during the Second World War, leaving behind drawings, notes, and lingering uncertainty. For decades, Spinosaurus existed as an outline rather than a full animal, a name attached to an idea that could not be fully tested. When new fossils were eventually discovered, they did not simplify the story. They complicated it. Spinosaurus grew into one of the most debated dinosaurs ever described, not because it was incomplete, but because it kept breaking expectations. At full size, Spinosaurus was enormous. Estimates suggest it may have reached length of 15 meters or more, making it potentially longer than any other known predatory dinosaur. But length alone does not explain its strangeness. The most visually striking feature was its sail. Rising from the animal's back was a series of elongated neural spines, forming a tall, narrow structure that ran along much of the spine. This sail may have reached heights of over 1.5 meters. It was not a small crest or a minor decoration. It dominated the animal's silhouette. What the sail was for remains debated. Possibilities include display, species recognition, thermoregulation, or some combination of these. What matters is that Spinosaurus carried it throughout its life, suggesting it played a meaningful role in how the animal lived and interacted with its environment. Then there is the snout. Unlike the blunt, bone-crushing skulls of many large theropods, Spinosaurus had a long, narrow snout lined with conical teeth. These teeth were not shaped for slicing through flesh or cracking bone. They were better suited for gripping slippery prey. The skull looked more like that of a crocodile than a typical dinosaur predator. That resemblance was not superficial. Fossil evidence suggests that Spinosaurus spent a significant amount of time around water. Its teeth, jaw shape, and skull proportions all point toward a diet that included large amounts of fish. Isotopic analysis of its bones supports this idea, showing chemical signatures consistent with aquatic feeding. Spinosaurus was not just visiting rivers and lakes, it was adapted to them. Its body tells the same story. Compared to other large theropods, Spinosaurus had shorter hind limbs. This made it less efficient as a fast runner on land. Its feet were broad, possibly webbed, increasing surface area for movement in water. Its bones were unusually dense, reducing buoyancy and helping the animal stay submerged rather than floating uncontrollably. Even the tail was different. Recent fossil discoveries revealed a tall, flattened tail with elongated spines and flexible structure, well suited for propulsion through water. Rather than acting as a counterbalance for running, the tail appears to have functioned as a swimming aid, generating thrust in side-to-side motions. Put together, these traits paint a picture of an animal that lived at the boundary between land and water. Spinosaurus was not fully aquatic in the way whales or dolphins are today. It still needed to breathe air and move on land. But it was far more at home in water than any other known large dinosaur. This makes Spinosaurus deeply unusual. Dinosaurs are often imagined as strictly terrestrial animals, adapted for running, chasing, and standing upright. Spinosaurus rejected that template. It specialized in a niche that no other large dinosaur seems to have occupied so fully. This specialization likely shaped its behavior. Rather than sprinting across open plains in pursuit of prey, Spinosaurus may have waded through rivers, waited along shorelines, or swum after large fish. Its long snout could snap sideways through water, reducing drag. Its teeth could grip struggling prey without needing to tear or crush. In this environment, speed on land mattered less than control in water. The sail towering above its back would have been visible from a distance, whether it served as a display, a signal to other Spinosaurus individuals, or something else entirely. It added to the animal's already dramatic presence. Imagine encountering this animal in its habitat. A long-bodied predator moving through shallow water, tail undulating, snout just above the surface, sail cutting a tall silhouette against the sky. It would not look like a hunter in pursuit. It would look like part of the landscape itself. Spinosaurus did not need to chase. It could wait. Its unusual anatomy likely reduced competition. Other large predators focused on land-based prey. Spinosaurus focused on aquatic resources, tapping into a food source that was abundant and relatively uncontested. This division of labor may explain how multiple giant predators could coexist in the same ecosystems. Each occupied a different niche, reducing direct conflict. Spinosaurus also challenges the idea that there is a single best way to be a large predator. It shows that size and power can be expressed through specialization rather than versatility. Its story is also a reminder of how dynamic scientific understanding can be. For much of the 20th century, Spinosaurus was imagined as a conventional bipedal hunter with an unusual sail. As new fossils appeared, that image slowly collapsed. Each new bone added detail but also forced revision. The animal became longer, heavier, more aquatic, and less suited to the role it had once been assigned. This ongoing revision is not a weakness of science, it is its strength. Spinosaurus is strange not only because of how it lived, but because it keeps revealing new information. It refuses to settle into a final, comfortable reconstruction. Each discovery reshapes the animal slightly, reminding us that deep time is complex and incomplete. In the end, Spinosaurus stands as one of the clearest examples of an animal that refused to fit the rules of its group. It was a dinosaur that swam, a predator that hunted fish, a giant that traded speed on land for control in water, a silhouette defined as much by its sail as by its jaws. Spinosaurus did not resemble what came before it, and it did not leave behind clear successors. It occupied a narrow slice of evolutionary possibility, thriving for a time in a world that allowed such an unusual combination of traits to succeed. When that world changed, Spinosaurus disappeared, leaving behind bones, questions, and an animal that continues to challenge assumptions. Even now, long after it slipped beneath ancient waters for the last time, Spinosaurus refuses to stand still. Therizinosaurus looked like a misunderstanding given bones. At first glance, it appeared to be a predator built from spare parts. Massive body, long neck, broad hips, and then the hands. Each arm ended in 3 enormous claws, some over 1 meter long, curved and sharp enough to look dangerous from any angle. For years after its discovery, Therizinosaurus puzzled scientists. Those claws were unlike anything seen in other dinosaurs of similar size. They looked like weapons. Naturally, early interpretations assumed they belonged to a fearsome carnivore. They did not. Therizinosaurus was a plant eater. Living around 70 million years ago during the late Cretaceous period, Therizinosaurus belonged to a strange group of dinosaurs called therizinosaurs. These animals were distant relatives of meat-eating theropods. Yet they had taken a dramatically different path. Instead of sharp teeth for tearing flesh, Therizinosaurus had small leaf-shaped teeth suited for cropping vegetation. Instead of a narrow, streamlined body for chasing prey, it had a wide torso and large gut, ideal for digesting tough plant material. Its posture was upright and bulky, not built for speed. So why the claws? The answer lies not in hunting, but in feeding. Therizinosaurus likely used its claws as tools rather than weapons. Their length and curvature would have been excellent for pulling branches closer, hooking vegetation, and stripping leaves from trees and shrubs. In a landscape filled with tall plants, having reach mattered. The claws allowed Therizinosaurus to access food that smaller herbivores could not. Its long neck worked with the arms, extending its feeding range both upward and outward. Rather than grazing close to the ground, Therizinosaurus could browse at multiple heights, reducing competition with other plant-eating dinosaurs. There's also evidence that the claws played a role in defense. While not designed for slashing attacks like those of predatory dinosaurs, their sheer size would have been intimidating. A full-grown Therizinosaurus standing upright could present a wall of curved blades between itself and any potential threat. This does not mean it fought regularly. Large herbivores often rely on deterrence rather than combat. Looking dangerous can be just as effective as being dangerous. Therizinosaurus also had strong forelimbs and a broad shoulder girdle, suggesting those arms were not fragile ornaments. They were weight-bearing, powerful structures, capable of sustained use. This supports the idea that the claws were actively involved in daily life, not carried purely for show. Its body adds further context. Therizinosaurus was tall and heavy, with powerful hind legs but limited agility. It was not built to flee quickly. In such a case, tools for defense and deterrence become more important. Standing ground, displaying size, and presenting formidable claws would have discouraged many predators from testing their luck. There is also a quieter possibility. Some scientists have suggested the claws may have played a role in social behavior, such as display or competition within the species. Large, visually striking features often serve multiple purposes in animals, from feeding to communication. While direct evidence is limited, the idea fits with what is seen in many modern herbivores that use body structures for more than one function. What makes Therizinosaurus especially striking is how completely it defies the stereotype of a theropod dinosaur. Theropods are often imagined as fast, lean hunters with sharp teeth and grasping hands. Therizinosaurus inherited the body plan of that group, then repurposed it entirely. It took arms meant for grasping prey and turned them into gardening tools. It took a lineage known for carnivory and filled it with plants. This kind of evolutionary reversal is rare, but not unheard of. Evolution does not erase ancestry. It modifies it. Therizinosaurus still carried the legacy of predatory ancestors in its skeleton, even as its lifestyle changed completely. The result was an animal that looked dangerous even when it was not acting aggressively. Therizinosaurus reminds us that appearances can mislead, especially when viewed through the lens of modern expectations. Sharp structures do not always mean meat, size does not always mean speed, and fearsome anatomy does not always point to violence. In its ecosystem, the Rhizinosaurus likely played a role similar to that of large browsing mammals today. It shaped vegetation, opened up feeding spaces for smaller animals, and moved slowly through its environment, more concerned with leaves than with conflict. Those claws, dramatic and unsettling as they were, served a peaceful purpose most of the time. Therizinosaurus did not evolve its claws to hunt. It evolved them to eat, to reach, to defend when necessary, and to survive in a crowded world filled with competition for food. It stands as one of the clearest examples that evolution does not follow simple rules. Sometimes the most intimidating tools belong not to predators, but to animals quietly pulling branches closer, one careful swipe at a time. Pachycephalosaurus looked like it had been designed around one idea, and that idea sat right on top of its head. Living around 70 million years ago in what is now North America, Pachycephalosaurus was a medium-sized dinosaur with a compact body, strong legs, and a skull unlike any other. Rising from the top of its head was a thick, rounded dome of bone, up to 25 centimeters thick at its center. It was not a crest. It was not a horn. It was a solid mass. From the moment the first skulls were discovered, that dome invited a single question. What was it for? The most intuitive answer was also the most dramatic. Pachycephalosaurus, it seemed, was built to headbutt. The rest of its body supports this idea. Pachycephalosaurus had a sturdy neck, reinforced vertebrae, and a posture that would have aligned the head, spine, and hips into a stable column. Its hind legs were strong, capable of delivering forward force. Its center of mass sat low and balanced. If an animal were going to collide head-first with something, this would be a sensible design. Bone structure inside the dome adds further intrigue. The interior was not solid all the way through. Instead, it contained a network of bony struts and dense tissue, a bit like a natural shock absorber. This internal architecture may have helped distribute forces during impact, reducing the risk of catastrophic injury. Modern animals offer a useful comparison. Bighorn sheep engage in headbutting contests that involve significant forces, yet their skulls and necks are adapted to absorb repeated impacts. Pachycephalosaurus may have filled a similar role in its ecosystem, using physical contests to establish dominance or compete for mates. However, the story is not quite that simple. Some researchers have pointed out that repeated high-speed head-on collisions could still be risky, even with a thick skull. There is also evidence of lesions and injuries on some Pachycephalosaurus domes, suggesting trauma did occur. Whether that trauma came from headbutting, accidental impacts, or interactions with predators remains debated. An alternative behavior has been proposed. Instead of full-speed head-on collisions, Pachycephalosaurus may have engaged in flank butting. In this scenario, individuals would strike each other's sides with their domed heads, aiming for ribs or hips rather than skull-to-skull contact. This would still reward a strong reinforced head while reducing the chance of brain injury. Either way, the dome was not decorative. It required energy to grow. It added weight. It altered balance. Evolution does not build such structures without reason. Whether used for headbutting, display, or a combination of behaviors, the dome clearly played a central role in how Pachycephalosaurus lived. Its diet was likely herbivorous, feeding on low-growing plants. This makes the dome even more interesting. Unlike predators that use weapons to subdue prey, Pachycephalosaurus invested heavily in a structure used primarily for interactions with its own species. This suggests a social component to its life. Visual display may also have mattered. A large rounded dome would have been visible from a distance, signaling maturity, health, or dominance. In many animals, physical contests are preceded by display. with actual combat serving as a last resort. Pachycephalosaurus may have followed a similar pattern. There is also evidence that the dome changed shape as the animal aged. Younger individuals appear to have flatter skulls, with the dome thickening over time. This supports the idea that the structure was linked to adulthood and social behavior rather than basic survival. Pachycephalosaurus was not the fastest dinosaur. It was not the largest. It did not possess claws or teeth designed for fighting. Instead, it focused its evolutionary investment into one remarkable feature. Its head became its statement. That focus tells us something about the pressures it faced. Competition among members of the same species can be just as important as avoiding predators. Securing territory, access to food, or mating opportunities can shape anatomy in powerful ways. Pachycephalosaurus reminds us that not all evolutionary arms races happen between predator and prey. Some play out within a species, driven by social dynamics and competition. There is also something quietly amusing about the idea. In a world filled with massive predators and towering giants, one dinosaur decided the solution was simple: make the head very thick, then see what happens. Whether Pachycephalosaurus charged headlong into rivals or used its dome more subtly, the result was an animal built around impact. Its skull was not an accident of anatomy. It was the centerpiece of its behavior. In the late Cretaceous, Pachycephalosaurus did not need claws or teeth to make an impression. It carried its strategy right on its head, and it used it in a way that ensured it would be remembered long after the rest of its body faded into stone. Microraptor looked like a dinosaur caught mid-experiment. Living around 120 million years ago during the early Cretaceous period, Microraptor was small, lightweight, and feathered from head to tail. At first glance, it resembled a bird-like dinosaur not much larger than a modern crow. But a closer look revealed something far stranger. Microraptor had 4 wings, not in the metaphorical sense, not in the sort of sense. Actual wings with long flight feathers attached to both its arms and its legs. Its forelimbs carried broad feathered surfaces as expected. But its hind limbs did too, forming a second pair of aerodynamic planes beneath the first. This made Microraptor unlike any flying animal alive today. Its body was covered in feathers, including long tail feathers that added stability and control. The feathers on its arms and legs were asymmetrical, the same shape seen in modern birds that fly, suggesting they were adapted for interaction with air rather than simple insulation or display. Microraptor was not running along the ground flapping uselessly. It was airborne. Exactly how it flew has been debated, but the consensus is that Microraptor was capable of gliding and possibly powered flight over short distances. It likely launched itself from trees, using gravity and lift together, moving between branches in forested environments. Several flight postures have been proposed. One suggests that Microraptor held its hind legs out to the sides, forming a biplane-like arrangement with forewings above and hindwings below. Another suggests a more staggered configuration, with the rear wings angled slightly backward. Either way, Microraptor was adapted to move through the air in a way that modern birds do not. Its skeleton supports this interpretation. The shoulder joints allowed a wide range of motion. The feathers were arranged to maximize surface area. The tail acted as a rudder, helping with balance and steering. Its claws suggest it could climb trees easily, positioning itself for aerial launches. Microraptor was not built for long-distance flight. It did not have the deep chest muscles or keeled breastbone seen in modern birds. Instead, it was optimized for short, controlled movements through cluttered environments. In a dense forest, that makes sense. Leaping from branch to branch, gliding down to the forest floor or escaping predators by dropping into open air would have been effective strategies. Flight did not need to be sustained, it needed to be useful. So why did this design not last? The answer lies in efficiency and constraint. Having 4 wings increases lift, but it also increases complexity. Coordinating 4 feathered surfaces requires precise control. The hind wings interfered with walking and running on the ground, limiting mobility when not airborne. Folding the rear wings neatly out of the way would have been awkward. Over time, evolution favoured a simpler solution. Birds that followed streamlined their design. The forelimbs became the sole wings, the hind limbs specialised for perching, walking and launching. This freed the legs from aerodynamic duty and allowed more efficient takeoff, landing and ground movement. In short, 2 wings were enough. Microraptor represents a stage where evolution had not yet settled on the most flexible compromise. It shows that flight did not emerge in a single clean step. There were multiple attempts, multiple arrangements, and multiple ways of getting off the ground. Some worked better than others. Microraptor's environment also played a role. As forests changed and birds became more capable flyers, competition increased. Animals that could fly farther, maneuver more easily, and land more safely had an advantage. The 4-winged configuration, while functional, was eventually outperformed. That does not mean Microraptor failed. For millions of years it survived, hunted, and reproduced successfully. It fed on small animals, likely including insects and small vertebrates, using its sharp teeth and claws. It navigated its world effectively using a body plan that seems strange only in hindsight. There is also something elegant about Microraptor's solution. Rather than radically reshaping its body, it extended an existing structure. Feathers were already present, limbs were already mobile. Microraptor simply used what it had in a new way. That kind of innovation is common in evolution. New functions often emerge from old parts. The fossils of Microraptor are among the most beautifully preserved dinosaur remains ever found, including clear impressions of feathers. They provide a rare glimpse into not just bones, but texture, shape, and even colour patterns. Some studies suggest Microraptor's feathers were iridescent, reflecting light in a way similar to modern crows. This adds another layer to its story. Microraptor may not only have flown, it may have shimmered while doing so. In the end, Microraptor stands as a reminder that the path to modern birds was not straight or simple. Flight was explored from multiple angles, tested in different forms, and refined through trial and error. Microraptor took to the air with 4 wings and showed that it could be done. That alone is remarkable. Its design did not persist, not because it was flawed, but because evolution found a cleaner solution later on. 2 wings offered more flexibility, less interference, and greater long-term success. Microraptor does not represent a mistake. It represents a possibility. For a brief span of deep time, forests were filled with small feathered dinosaurs gliding between trees on 4 wings, navigating a world where flight was still new and full of options. Microraptor simply chose one of them, and for a while it worked beautifully. Quetzalcoatlus did not look like it should be able to fly. When standing on the ground, it would have been taller than a giraffe, with a long neck held high above the body, and a sharp, elongated beak extending forward. Its wings, when folded, rested like enormous walking limbs at its sides. This was not a delicate glider perched in trees. It was a towering animal that walked confidently across open landscapes. And yet, Quetzalcoatlus could take to the air. Living around 68 million years ago during the late Cretaceous period, Quetzalcoatlus was one of the largest pterosaurs ever discovered and the tallest flying animal known to science. When fully upright, it may have stood 5 to 6 meters tall. When it spread its wings, the span likely reached 10 to 11 meters, rivaling the width of a small airplane. Despite these extreme dimensions, Quetzalcoatlus was not a clumsy giant weighed down by its size. Its skeleton was remarkably light, built from hollow bones reinforced by internal struts. This design provided strength without excessive mass, a necessity for any animal that hoped to leave the ground. Quetzalcoatlus did not walk on two legs like a bird. It moved on all fours when on land, using its long wing fingers as front limbs. This posture made it stable and efficient, allowing it to travel across flat terrain without dragging its wings or struggling to balance. This detail matters because it changes how the animal lived. Rather than spending its time perched or clinging to cliffs, Quetzalcoatlus likely walked extensively. Its proportions suggest a lifestyle similar to a modern ground hunting bird, but on a far grander scale. It may have stalked across floodplains and open environments, scanning for small animals to catch with its beak. Its skull was long and narrow, with no teeth, well suited for grasping prey whole. Fossil evidence and biomechanical modelling suggest it fed on small vertebrates, carrion, and possibly fish, depending on availability. It did not need to tear flesh. It could simply pick up food and swallow it. This makes Quetzalcoatlus less like a soaring seabird and more like a walking predator that happened to fly. The question that has fascinated scientists for decades is how an animal of this size could get airborne at all. The answer lies in how it launched. Unlike birds, which rely primarily on their hind legs to jump into the air, Quetzalcoatlus used a four-limbed launch. Its powerful forelimbs pushed against the ground, vaulting the body upward before the wings began their first full strokes. This technique distributed the force across the strongest muscles in the body and reduced the strain on the hind legs. Studies of pterosaur anatomy suggest this launch method was not only possible, but efficient. Once airborne, Quetzalcoatlus could use its vast wings to glide for long distances, conserving energy by riding air currents. It didn't need to flap constantly. Its size worked in its favour. Large wings generate lift efficiently, allowing sustained flight with relatively low effort once altitude is gained. Quetzalcoatlus likely spent much of its time soaring, covering large areas in search of food. When it landed, it did so deliberately, folding its wings and returning to a stable four-limbed stance. This dual lifestyle sets it apart from modern flying animals. Birds are often awkward on the ground. Bats cling and hang. Quetzalcoatlus appears to have been comfortable both walking and flying, moving seamlessly between the two. Its neck was long and flexible, allowing it to strike downward with speed and precision. Its head crest, if present, may have served for display or species recognition, though evidence remains incomplete. Whatever its exact function, the crest added to the animal's already dramatic profile. There is a tendency to think of Quetzalcoatlus as a flying impossibility, a creature stretched beyond realistic limits. But the fossil record suggests otherwise. Its proportions are consistent. Its joints show signs of repeated stress and use. Its bones bear the marks of a real animal living an active life, not a fragile glider one misstep away from collapse. It existed at the same time as large predatory dinosaurs, sharing the landscape rather than avoiding it. Its size likely offered some protection. Few predators would challenge an animal that tall, especially one capable of launching itself into the air if threatened. Quetzalcoatlus also challenges assumptions about flight itself. Flight is often imagined as the domain of small, lightweight creatures. Quetzalcoatlus demonstrates that with the right design, flight can scale upward far beyond what intuition suggests. Eventually, like all non-avian pterosaurs, Quetzalcoatlus disappeared, The mass extinction at the end of the Cretaceous closed the chapter on giant flying reptiles. Birds, already present, continued on a different path, occupying smaller niches and surviving the global upheaval. Quetzalcoatlus left no direct descendants. What it left instead was perspective. It shows that the sky was once shared with animals that walk like giraffes, launched like catapults, and soared with wings broader than many rooms. It reminds us that the limits we imagine for nature are often shaped by the present, not by the full range of what has existed. Quetzalcoatlus was not a concept or an experiment. It was an animal that walked, fed, launched, flew, landed, and lived in a world that allowed such extremes to function. For a time, the tallest thing on the ground could also be the largest thing in the sky, and it did both with ease. Titanoboa lived in a world that no longer exists. It appeared just a few million years after the dinosaurs vanished, during the early Paleocene, when the planet was warmer, wetter, and far more humid than today. The forests of what is now northern South America were dense, swampy, and steaming. Rivers moved slowly through thick vegetation. The air itself held heat. This was a greenhouse Earth, and in that world Titanoboa became the largest snake that ever lived. At full size, Titanoboa stretched more than 13 meters in length and weighed well over a metric ton. That made it longer than a city bus and heavier than many modern cars. It was not simply a big snake. It was a fundamentally different scale of snake, operating at the upper limit of what a cold-blooded animal could achieve. Its body was thick and muscular, built for power rather than speed. Each movement would have displaced water and vegetation with ease. In the slow-moving rivers and wetlands it inhabited, Titanoboa would have been impossible to ignore. The reason Titanoboa could grow so large comes down to temperature. Snakes, like all reptiles, rely on external heat to regulate their body processes. The warmer the environment, the more efficiently their muscles, digestion, and metabolism can function. In the Paleocene tropics, average temperatures were several degrees higher than today, with little seasonal variation. That constant warmth removed a major constraint. In cooler climates, a snake of Titanoboa's size would struggle to digest food, move effectively, or maintain basic bodily functions. In a hot, stable environment, those problems faded. The Earth itself supported the animal's growth. Titanoboa's habitat was dominated by large rivers, floodplains, and coastal swamps. Fossils were discovered in ancient river deposits, suggesting a lifestyle closely tied to water. This makes sense. Water helps support weight, reducing stress on the body, and provides access to large prey. Titanoboa was not a fast-moving ambush hunter in the style of many modern snakes. Its size made speed unnecessary. Instead, it likely relied on stealth, patience, and overwhelming strength. Its primary prey probably included large fish, turtles, and crocodilian relatives. Early crocodilians in this region were already sizable, but Titanoboa was larger still. Fossil evidence suggests it could overpower animals that would be apex predators in any other context. Hunting likely took place in water or at the water's edge. Titanoboa could remain mostly submerged, with only part of its head exposed, waiting for movement. When prey came within reach, the strike would have been sudden and decisive. Unlike venomous snakes, Titanoboa killed through constriction. Its coils wrapped around prey, tightening with each exhalation, cutting off blood flow rather than air. This method scales well with size. The larger the snake, the more effective the constriction. Titanoboa's body was perfectly suited for this. Thick vertebrae, massive ribs, and powerful muscles allowed it to exert enormous pressure. Once caught, escape would have been nearly impossible. Despite its size, Titanoboa was not a reckless monster roaming the landscape. Large animals tend to conserve energy. It likely fed infrequently, consuming massive meals that sustained it for long periods. After feeding, it may have spent days or weeks resting, digesting slowly in the warmth. Its skull was proportionally large but not exaggerated. This suggests it swallowed prey whole, as snakes do today, rather than tearing or crushing. Its jaws could open wide enough to accommodate large animals, aided by flexible ligaments rather than fused bone. What makes Titanoboa especially striking is how quickly it appears in the fossil record. Dinosaurs vanish, and almost immediately Titanoboa emerges. This tells us something important. Large body size did not disappear with the dinosaurs. It was suppressed by circumstance. Once those constraints lifted, size returned through different lineages. Mammals would eventually grow enormous too, but they took time. Titanoboa arrived early, taking advantage of heat and ecological space before mammals fully expanded into large-bodied roles. This does not make Titanoboa an anomaly. It makes it a signal. It signals just how extreme Paleocene conditions were. By studying Titanoboa's size, scientists can estimate past temperatures. The logic is simple. A snake that large could only function if average temperature stayed above a certain threshold year-round. Titanoboa's body becomes a climate record. Using comparisons with modern snakes and their temperature limits, researchers have estimated that mean annual temperatures in its habitat were several degrees warmer than current tropical averages. In other words, Titanoboa confirms that the Paleocene tropics were not just warm, but persistently hot. There is also a humbling perspective here. Titanoboa did not rule its world because it was uniquely clever or aggressive. It ruled because the environment allowed it to exist. Its dominance was a partnership between biology and climate. When the climate changed, Titanoboa disappeared. Titanoboa did not fail. The world simply moved out from under it. There is something quietly unsettling about that. Titanoboa reminds us that the boundaries of nature are flexible. What seems impossible today may have been routine before. A snake longer than a bus feels unreal only because the current Earth no longer permits it. In the Paleocene rainforest, Titanoboa was not mythical. It was not exceptional. It was simply the largest thing in a world that allowed large things to exist. It moved through dark water beneath tangled branches. It waited. It struck. And then it rested, digesting slowly in the heat, surrounded by a planet that, for a brief time, was warm enough to let a snake become a giant. Titanoboa did not just live in a greenhouse world, it was built by it. Paraceratherium did not need horns to dominate the landscape. Living between roughly 34 and 23 million years ago, during the late Eocene and early Oligocene, Paraceratherium was the largest land mammal that ever lived. It belonged to the rhinoceros family, but it would not have looked much like any rhino alive today. There was no horn, no squat tank-like body. Instead, Paraceratherium stood tall, with long legs, a deep chest, and a neck that lifted its head high above the ground. When fully grown, it may have stood more than 5 meters tall at the shoulder, with its head reaching even higher. Estimates suggest it weighed well over 15 tons. That made it taller than a giraffe and heavier than several modern elephants combined. Despite this immense size, Paraceratherium was not slow or clumsy. Its body was built for steady, efficient movement across vast open landscapes. Long limbs carried its weight with relatively slender bones, arranged in a column-like posture that minimized energy loss. Each step was deliberate but not labored. This was an animal designed to travel. Paraceratherium lived in wide, semi-arid regions with scattered trees and open woodland. These environments suited a giant browser. With its long neck and elevated head, Paraceratherium could feed on leaves and branches far above the reach of most other herbivores. It did not compete with smaller animals for ground-level plants. It occupied a feeding zone of its own. Its skull was elongated with large nasal openings that suggest a flexible upper lip or short trunk. Rather than using horns or tusks, Paraceratherium relied on reach and bulk. It could strip leaves from tall trees, moving slowly from one feeding site to the next. Feeding at this scale required constant intake. An animal weighing tens of thousands of kilograms needs enormous amounts of food each day. Paraceratherium likely spent most of its waking hours eating, much like modern elephants and giraffes. Its digestive system would have been large and complex, capable of breaking down tough plant material through fermentation. This slow, steady feeding strategy made sense. With few natural predators capable of threatening a fully grown Paraceratherium, there was little need for speed or aggression. Size itself was the defense. Predators of the time, including large carnivorous mammals, may have posed a risk to juveniles. Adults, however, would have been effectively untouchable. Challenging an animal that tall and heavy would have been extremely dangerous and energetically costly. Paraceratherium's movement reflects this confidence. Its limbs were built for endurance rather than bursts of speed. It could cover long distances efficiently, migrating between feeding areas as vegetation shifted with seasons or climate changes. Its height allowed it to see over long distances, offering early warning of any potential threats. Instead, Paraceratherium invested in height. That height shaped its entire lifestyle. It fed differently. It moved differently. It interacted with its environment in ways no other mammal could. Trees that might have been out of reach to other herbivores were simply part of its daily diet. There is also evidence that Paraceratherium lived in relatively small groups or even solitary. Large animals often spread out to reduce competition for food. A single Paraceratherium could strip significant foliage from an area, making close neighbours impractical. Its reproduction would have been slow. Long gestation periods, extended juvenile development, and low birth rates are typical of very large mammals. This made Paraceratherium vulnerable to environmental change. While size protects against predators, it offers little defense against shifting climates and shrinking habitats. And the climate did change. As the Earth cooled during the Oligocene, forests gave way to more open grasslands in many regions. Tall browsing niches shrank. Food sources changed. The environments that supported Paraceratherium's immense size became less common. Smaller, more flexible herbivores adapted more easily. Paraceratherium, built for a specific world, gradually disappeared. What makes Paraceratherium especially compelling is that it shows how far mammalian size can be pushed under the right conditions. Mammals regulate their own body temperature, which allows them to live in cooler environments than reptiles. But this comes at a cost. Larger mammals require more food, more time, and more stable ecosystems. Paraceratherium represents a peak where those demands were met. Its success was not accidental. It was the result of millions of years of gradual scaling, with each generation pushing slightly larger, slightly taller, as long as the environment allowed it. There is also something quietly elegant about Paraceratherium. It was not aggressive. It did not rely on sharp weapons or dramatic behavior. It simply grew until nothing else could compete with it on its terms. In doing so, it reshaped its environment. Large browsers influence plant growth, seed dispersal, and landscape structure. Paraceratherium likely played a role similar to modern megaherbivores, shaping ecosystems simply by eating and moving through them. Its extinction reminds us that even the most imposing animals are temporary. When conditions shift beyond what a body plan can tolerate, size becomes a liability rather than an advantage. Paraceratherium was not replaced by a larger mammal. Nothing bigger ever took its place. Instead, the ceiling lowered. Today, elephants stand as the largest land mammals, impressive but still far smaller than Paraceratherium. The world they inhabit cannot support giants on that earlier scale. Paraceratherium stands as a reminder of a time when land itself could carry something taller than a giraffe and heavier than imagination suggests. It walked across open plains, lifted its head into the trees, and fed calmly in a world that allowed mammals to reach truly monumental size. For a while, the Earth made room for a mammal that large, and Paraceratherium filled it. Glyptodon looked like a mammal that had decided compromise was no longer an option. Living from around 2 million years ago until roughly 11,000 years ago, Glyptodon roamed the grasslands and open woodlands of South America. It was related to modern armadillos, but that relationship becomes hard to believe once size enters the picture. Where today's armadillos can be picked up with 2 hands, Glyptodon weighed as much as a small car and stood low to the ground beneath a vast dome of armor. This was not a flexible shell, it was a solid structure. Glyptodon's body was encased in a massive rigid carapace made of thousands of interlocking bony plates fused together into a single dome. Unlike modern armadillos, Glyptodon could not roll into a ball. It did not need to. Its shell was already complete, continuous, and immovable. The armor covered the back, sides, and much of the underside, leaving little exposed. Even the head was partially shielded by thick bone. The tail, rather than being a vulnerable extension, was often reinforced with heavy rings of bone, and in some species ended in a blunt club-like structure. This was defense taken to an extreme. Glyptodon was a slow-moving herbivore. Its legs were short and sturdy, built to support weight rather than speed. Its body sat low, making it difficult for predators to get underneath the shell. Running was not part of its survival strategy. Standing ground was. The environment Glyptodon lived in helps explain why this approach worked. During the Ice Ages, South America supported a diverse community of large predators, including saber-toothed cats and giant carnivorous mammals. For a slow, bulky herbivore, escape would have been unlikely. So Glyptodon did not try to escape. Instead, it became difficult to kill. The armor was not just thick, it was well designed. The bony plates were arranged to distribute force across the shell, reducing the impact of bites or strikes. Attacking from above would have been nearly pointless. Biting through the carapace would have required tremendous force, well beyond what most predators could deliver. Predators may have targeted juveniles or attempted to attack the limbs, but even then the risk would have been high. A full-grown Glyptodon was a poor return on investment. Too much effort, too much danger, too little reward. That imbalance likely kept Glyptodon relatively safe. Its head and teeth tell a calmer story. Glyptodon fed on low-growing vegetation, using blunt, grinding teeth suited for processing tough plant material. It grazed steadily, moving slowly across the landscape, consuming grasses and other hardy plants. Digestion would have been slow, supported by a large gut capable of breaking down fibrous food. Like many large herbivores, Glyptodon likely spent much of its day feeding and resting, conserving energy rather than expending it. There is something quietly impressive about this lifestyle. Glyptodon did not rely on intelligence, speed, or aggression. It relied on engineering. Its shell grew over its lifetime, thickening and expanding as the animal matured. Juveniles were smaller and more vulnerable, but as they grew, protection increased. By adulthood, the shell was an integral part of the animal's identity, not an accessory. This investment came at a cost. Carrying so much bone required energy. Growing and maintaining armor meant resources diverted away from speed, agility, and reproduction. Evolution accepted those trade-offs because the payoff was survival. And for a long time it worked. Glyptodon survived multiple climate shifts and coexisted with large predators for hundreds of thousands of years. It was a stable presence in its ecosystems, slow but resilient. Its downfall came not from predators with teeth and claws, but from a new kind of threat. As humans arrived in South America, the balance changed. A slow-moving animal with predictable habits and enormous amounts of meat became an attractive target. There is evidence that early humans hunted Glyptodon, and in some cases may have even used its shell as shelter. Unlike natural predators, humans could exploit patience, tools, and coordination. Armor that stopped bites did nothing against strategy. Combined with changing climates at the end of the last ice age, this pressure proved too much. Glyptodon disappeared, joining many other large mammals in a wave of extinctions. What remains is an animal that feels almost exaggerated, like a concept pushed to its limit. Glyptodon shows that mammals are capable of extreme solutions. While many mammals rely on speed or social behavior to survive, Glyptodon chose isolation and fortification. It became a living bunker, moving slowly through open landscapes, trusting that nothing would be able to force its way inside. There is certain honesty to that approach. No tricks, no bluffs, just bone, weight, and time. In its world, Glyptodon did not need to be clever. It did not need to be fast. It needed only to endure. And for tens of thousands of years it did exactly that, carrying its shelter wherever it went, a mammal that turned itself into a tank and lived long enough to prove the idea worked. Megatherium moved through its world without urgency. Living from around 2 million years ago until roughly 11,000 years ago, Megatherium was a giant ground sloth that inhabited much of South America, and later parts of North America as well. It was related to the small tree-dwelling sloths alive today, but the resemblance was mostly theoretical. Megatherium was enormous, weighing several tons and standing taller than the human when upright. Despite that size, it lived slowly, deliberately, and very successfully. At rest, Megatherium walked on all fours, its body supported by thick limbs and massive claws that curved inward. Those claws were not used for hunting. Instead, they shaped how the animal moved. Like modern sloths, Megatherium walked on the sides of its feet to keep the claws from digging into the ground. A posture that looks awkward, but works well at low speeds. Speed was never the goal. Megatherium fed primarily on plants. Its skull and teeth were built for grinding tough vegetation rather than cutting flesh. It likely consumed leaves, branches, and possibly roots, processing large quantities of food each day. A large gut and slow digestion allowed it to extract nutrients efficiently from fibrous plant material. This feeding strategy pairs naturally with the slow pace of life. Megatherium did not need to chase prey or flee quickly. It needed time, stability, and access to food. One of the most striking behaviors inferred from its skeleton is its ability to stand upright. When Megatherium rose onto its hind legs, it could balance using its powerful tail as a third support, forming a stable tripod. In this position, it stood as tall as a bear and could reach vegetation far above the ground. Standing upright also changed how it interacted with its environment. In this posture, Megatherium could pull down branches using its claws, bringing food within reach. The claws acted as hooks, not weapons, allowing it to manipulate trees and shrubs rather than tear into animals. This behavior would have given it access to food sources unavailable to smaller herbivores. The upright stance may also have served a defensive purpose. When standing tall, Megatherium presented an imposing silhouette. Combined with its size, claws, and strength, this would have discouraged many predators from approaching. Although it was slow, Megatherium was not helpless. Its forelimbs were heavily muscled, capable of delivering powerful swipes if threatened. The claws, while primarily used for feeding, could have caused serious injury if used defensively. Few predators would have wanted to test that combination of size and strength. In ecosystems that included large carnivores such as saber-toothed cats, Megatherium relied on deterrence rather than escape. Like many large herbivores, its best defense was being too costly to attack. There has been debate about whether Megatherium may have occasionally consumed meat. Some studies have suggested that its strength and claws could have allowed it to scavenge or even prey on smaller animals. However, its teeth and digestive system are most consistent with a primarily plant-based diet. If meat was ever consumed, it was likely rare and opportunistic rather than central to its lifestyle. What is clear is that Megatherium succeeded without haste. Its bones show signs of long life. Its population spread widely across varied environments, from grasslands to forest edges. This flexibility suggests that slow does not mean fragile. With the right body plan, slowness can be a strength. Large size reduces the number of predators. Slow metabolism reduces energy demands relative to mass. A steady, predictable routine minimizes risk. Megatherium embodied all of these advantages. There is also something important about how Megatherium used time. It likely spent much of its day feeding and resting, conserving energy rather than expending it. In environments where food was abundant but competition existed, this steady approach paid off. Its success lasted for hundreds of thousands of years. Megatherium did not vanish because its strategy stopped working. It vanished because the world around it changed. As climates shifted at the end of the last ice age, vegetation patterns altered. More importantly, humans arrived in the same regions Megatherium inhabited. Slow, predictable animals with large bodies became targets. Strength and claws offered little protection against coordinated hunting and tools. Like many large mammals of the time, Megatherium could not adapt quickly enough to this new pressure. What remains is an animal that challenges assumptions about survival. Megatherium shows that life does not need to be fast to be effective. It does not need sharp teeth or complex strategies. Sometimes success comes from size, patience, and a body built to make the most of abundant resources. In a world that often rewards speed and aggression, Megatherium followed a different path. It lived slowly, fed steadily, and stood tall when it needed to. For most of its existence, that was enough. It walked deliberately across ancient landscapes, rising like a bear when reaching for food, carrying its weight with calm confidence. It did not rush. It did not need to. Megatherium proves that in evolution, there is more than one way to thrive. The tuatara does not behave like a survivor clinging to the past. It behaves like an animal that knows exactly where it belongs. Found only in New Zealand today, the tuatara looks at first glance like a lizard. Scaly skin, long tail, low spreading posture. For a long time, that similarity led people to treat it as an odd lizard that somehow escaped extinction. It is not a lizard. The tuatara belongs to a completely separate branch of reptiles, one that split away from the ancestors of lizards and snakes more than 250 million years ago. Every other member of that group vanished long ago. The tuatara did not. That does not make it primitive, it makes it distinct. In its daily life, the tuatara is calm, deliberate and well adapted to its environment. It is mostly nocturnal, emerging at dusk to hunt insects, worms, small reptiles, and seabird chicks. It does not rush. It waits, watches, and strikes when the moment is right. Its metabolism is slow, even by reptile standards. Tuatara can function at temperatures that would leave many other reptiles sluggish or inactive. They remain active in cool conditions, sometimes at temperatures just above freezing. This tolerance allows them to thrive in environments where competitors struggle. That slow pace extends to nearly every aspect of their biology. Their teeth offer a good example. Unlike most reptiles, tuatara do not replace their teeth. Instead, their teeth are fused directly to the jawbone. Over time, those teeth wear down. Older tuatara eventually rely on hardened ridges of bone to process food. This sounds like a disadvantage, but it fits their life perfectly. Their diet does not require sharp cutting edges. Their feeding is measured. Their wear rate matches their lifespan. Even their skull is unusual. Tuatara retain a flexible joint in the upper jaw that allows slight movement during biting. This gives them a strong, precise grip when capturing prey. It is not flashy, but it works. One of the most talked about features of the tuatara is the so-called third eye, a light sensitive organ located on the top of the head. In hatchlings, it is visible beneath thin skin. In adults, it becomes covered by scales. Again, practical rather than dramatic. Tuatara also show unusual reproductive patterns. Females may reproduce only once every several years, laying eggs that take more than a year to hatch. That is an exceptionally long incubation period for a reptile. This slow reproduction makes tuatara vulnerable to sudden environmental change. It also means that when conditions are stable, populations can persist for extraordinary lengths of time. For millions of years, that stability existed. The tuatara's success is not due to outcompeting others through speed or aggression. It comes from occupying a narrow, well-defined niche and staying there. While other reptile groups diversified rapidly and spread across the globe, the tuatara remained focused. When global changes wiped out its relatives, the tuatara endured in isolated environments where competition was limited. There is a temptation to describe the tuatara as unchanged, as if it simply froze in time. That idea is misleading. Genetic studies show that tuatara continue to evolve. Their pace is slow, but it is real. They adapt within their framework rather than reinventing themselves. The tuatara of today is not identical to its ancient ancestors. It is a modern animal, shaped by modern pressures, using a body plan that has proven durable. That durability is the key. Evolution does not reward novelty alone. It rewards what works. The tuatara's design works extremely well for its lifestyle. There has been no pressure strong enough to force it down a different path. Humans, unfortunately, introduced new pressures. Habitat loss and invasive species threaten tuatara populations. Conservation efforts have since helped stabilize numbers, protecting them on offshore islands and managed reserves. These efforts are not about preserving a fossil. They're about protecting a living species that still fills its role. That quiet confidence is part of what makes the tuatara so remarkable. It stands as a reminder that survival does not always mean constant change. Sometimes it means finding a way of life that fits so well it carries you through mass extinctions, shifting continents, and the rise and fall of entire animal groups. The tuatara is not a leftover. It is a specialist from a forgotten branch still doing exactly what it has always done, in a world that finally learned how rare that kind of persistence truly is. For a long time, the coelacanth was considered a finished story. Its fossils appeared in rocks more than 400 million years old, stretching forward through deep time and then stopping abruptly around 66 million years ago. When the dinosaurs vanished, the coelacanth seemed to vanish with them. Paleontology textbooks quietly closed the chapter, another ancient lineage gone. Then, in 1938, a fishing trawler off the coast of South Africa hauled up something unexpected. Among the catch was a large blue-grey fish with thick, fleshy fins and a body shape that looked more at home in stone than in seawater. When it reached the attention of scientists, disbelief followed quickly. The coelacanth was not supposed to exist, but it did. That moment cemented the coelacanth's reputation as the fish that refused to disappear. Since then, it has often been described as a living fossil, a phrase that sounds impressive but misses the reality. The coelacanth is not frozen in time, it is alive, active and very much a modern animal. Today, coelacanths are known from deep waters off the coasts of Africa and Indonesia. They live hundreds of meters below the surface, where sunlight barely penetrates and temperatures remain stable. This environment helps explain why they escaped notice for so long. They were never gone. They were simply out of sight. Coelacanths are large fish, often reaching 2 meters in length. Their bodies are thick and muscular, with a distinctive 3-lobed tail that sets them apart from most other fish. But the most famous feature is their fins. Unlike the thin, ray-supported fins of most fish, coelacanth fins are fleshy and limb-like, with bones arranged in a pattern that resembles the early blueprint of arms and legs. These fins move in a slow, coordinated way, almost like a walk through water rather than a swim. This movement is not fast. It is controlled and deliberate. Coelacanths are not pursuit predators. They drift, hover, and maneuver gently near rocky slopes and underwater caves, feeding on smaller fish and cephalopods. Their hunting style relies on patience and positioning rather than speed. Inside the coelacanth's skull is another unusual feature. It has a movable joint that allows the front of the skull to lift slightly during feeding, increasing gape and suction. This mechanism helps it capture prey efficiently without needing rapid strikes. There is also the matter of the coelacanth's brain, or rather the space where a brain might be expected. In adult coelacanths, the brain occupies only a small portion of the skull cavity. The rest is filled with fatty tissue. This is not a sign of simplicity or failure. It reflects a lifestyle that does not demand rapid processing or constant sensory overload. The coelacanth lives slowly and its body reflects that. The coelacanth did not remain unchanged because it could not evolve. It remained recognizable because its environment rewarded consistency. Genetic studies show that coelacanths have continued to evolve, just at a slower pace than animals living in more variable habitats. Change still happens. It is simply measured in longer spans of time. The coelacanth also plays an important role in understanding vertebrate evolution. Its fin structure provides insight into how early fish began transitioning toward life on land. This does not mean the coelacanth is an ancestor of land animals. It is a cousin, preserving features that help illuminate how those transitions occurred. This distinction matters. The coelacanth is not a missing link waiting to become something else. It is a successful endpoint in its own right. There is a tendency to treat animals like the coelacanth as evolutionary holdovers, as if they somehow fail to keep up. That framing misses the point entirely. Evolution does not reward novelty for its own sake. It rewards survival. The coelacanth has survived multiple mass extinctions, continental shifts, and ocean changes by staying within a niche that remained relatively untouched. Deep, stable waters shielded it from many of the pressures that reshaped life closer to the surface. That refuge came with a cost. Small populations and slow reproduction make coelacanths vulnerable to modern threats. Accidental capture by deep-sea fishing operations has posed risks, leading to conservation efforts aimed at protecting known populations. These efforts are not about preserving a curiosity. They are about protecting a species that still fills its ecological role. Seeing a living coelacanth is unsettling in a quiet way, not because it is monstrous or strange, but because it collapses time. An animal once known only from fossils moves its fins, opens its mouth, and drifts through water as it has for millions of years. The coelacanth did not return from extinction. It never left. Its story reminds us that absence from human awareness is not the same as absence from the world. Many lineages do not vanish dramatically. They retreat into places we rarely look. The coelacanth endures not as a relic, but as a living answer to a simple question. What happens when an animal finds a way of life that works well enough for long enough that the planet never quite manages to push it out? In the quiet depths of the ocean, the coelacanth continues to provide that answer, one slow, deliberate movement at a time. The horseshoe crab does not look like it belongs to the present. It moves slowly along shallow coastal waters, its rounded shell gliding over suggesting something ancient and deliberate. Its long, pointed tail follows behind, not as a weapon, but as a stabilizer, helping it right itself if overturned. From above, it resembles a relic. From below, it reveals a design that has endured for hundreds of millions of years. Horseshoe crabs first appeared more than 400 million years ago. Since then, they have survived multiple mass extinctions, shifting continents, changing sea levels, and dramatic swings in climate. While countless lineages rose and fell, the horseshoe crab persisted, not by being fast, not by being clever, but by being extremely well designed. Despite the name, horseshoe crabs are not true crabs. They are more closely related to spiders and scorpions than to crustaceans. Their bodies divided into three main parts: a broad protective shell, a hinged middle section, and the long tail spine known as a telson. That shell is the key. The horseshoe crab's carapace is thick, smooth, and curved, forming a natural shield that protects vital organs from above. Predators find little to grip. Teeth and claws slide off its surface. Attacking from the top is difficult and unrewarding. Underneath, things get more interesting. Beneath the shell, horseshoe crabs have multiple pairs of legs, each adapted for specific tasks. Some are used for walking, others help manipulate food. Specialized structures near the mouth grind prey before ingestion. It is a compact, efficient system, hidden safely beneath armor. Horseshoe crabs feed on worms, mollusks, and small invertebrates, rooting through sediment to uncover meals. They do not chase, they do not ambush, they simply move forward, steadily processing the environment as they go. This feeding style is important. Horseshoe crabs do not rely on a single food source. They are generalists, able to consume whatever small prey is available in their habitat. That flexibility makes them resilient when conditions change. Their reproduction is equally pragmatic. During spawning seasons, horseshoe crabs gather in large numbers along sandy beaches. Females lay thousands of eggs, which males fertilize externally. Many of those eggs become food for birds and fish, but enough survive to maintain populations. High output balances high loss. Their development is slow but steady. Juveniles resemble miniature adults, molting repeatedly as they grow. Each molt allows the animal to increase in size while retaining the same basic body plan. No radical redesign is needed. The shape already works. One of the most remarkable features of horseshoe crabs lies in their blood. Unlike human blood, which uses iron-based hemoglobin, horseshoe crab blood relies on copper-based hemocyanin, giving it a blue color. This blood is exceptionally sensitive to bacterial contamination. Even tiny amounts of bacterial toxins trigger clotting. This sensitivity has made horseshoe crab blood invaluable in modern medicine, where it is used to test the safety of vaccines, implants, and medical equipment. The same property that helped horseshoe crabs survive in microbe-rich environments now helps protect human health. This is persistence in an unexpected form. From an evolutionary perspective, the horseshoe crab succeeds because it avoids extremes. It is not specialized to a narrow niche. It does not depend on complex behaviors. Its sensory systems are sufficient rather than extravagant. Its body is robust rather than refined. When mass extinctions occur, specialists often vanish first. Generalists with durable designs last longer. The horseshoe crab exemplifies this principle. It does not need to be the best at anything. It only needs to be good enough at many things consistently over long periods of time. That said, persistence does not mean invulnerability. In recent history, horseshoe crab populations have faced pressure from habitat loss, overharvesting, and medical bleeding practices. Conservation efforts now aim to balance human use with population stability, recognizing that an animal which survived natural catastrophes can still be pushed toward decline by modern activity. Watching a horseshoe crab move along the shore, there is nothing dramatic about it. No speed, no display, no aggression, just steady motion, armor catching the light, legs working beneath the shell. That quiet competence is the reason it is still here. The horseshoe crab did not outcompete its rivals through innovation. It outlasted them through reliability. Its design solved the basic problems of survival early on, and the solutions remained valid as the world changed around it. While entire ecosystems collapsed and reformed, the horseshoe crab continued doing what it had always done, moving through shallow waters, feeding, reproducing, and enduring. It is not unchanged because it stopped evolving. It is unchanged because it never needed to start over. The horseshoe crab stands as a reminder that in evolution, the longest-lasting designs are often the simplest ones that refuse to break. Lungfish live in places where water cannot be trusted. They inhabit rivers, floodplains, and shallow pools that appear generous during wet seasons, and then quietly betray everything living in them when drought arrives. Oxygen drops, water warms, ponds shrink into mud. Most fish die, lungfish do not. They survive by doing something that feels like a contradiction. They breathe air. Lungfish first appeared more than 400 million years ago, and remarkably, they're still alive today. Modern species live in Africa, South America, and Australia, each adapted to environments where conditions can swing from abundance to disaster within months. Their defining feature is not speed or size, but flexibility. Inside a lungfish's body are true lungs, organs capable of extracting oxygen directly from air. These lungs are not decorative or occasional backups. In many species they are essential. When oxygen levels in water fall too low, lungfish surface and breathe just like terrestrial animals. This ability changes everything. Most fish rely entirely on gills, which only work efficiently when water is well oxygenated. Lungfish can switch strategies. They still have gills, but they are no longer dependent on them. When water becomes hostile, lungfish simply bypass the problem. Some species take this adaptation even further. African lungfish are famous for their ability to survive complete drought. When their pools begin to dry, they burrow into the mud and secrete a thick layer of mucus around their bodies. This mucus hardens into a cocoon, sealing moisture inside and slowing metabolism to a crawl. In this state, the lungfish enters a form of dormancy called estivation. While encased in dried earth, the lungfish breathes air through a small opening, sustaining itself for months or even years without food or free water. Its heart rate slows, its energy use drops, its body waits. When rains return, the mud softens, the cocoon dissolves, and the lungfish resumes life as if nothing happened. This is not a last-ditch emergency response. It is a routine part of the lungfish life cycle in harsh environments. Their bodies reflect this unusual lifestyle. Lungfish have elongated, flexible bodies and fleshy fins supported by bones rather than thin rays. These fins are not used for fast swimming. Instead, they allow lungfish to prop themselves up, maneuver along the bottom, and even move short distances across damp ground. Movement is slow, deliberate, and economical. Lungfish do not chase prey. They feed on invertebrates, small fish, and plant material, using crushing tooth plates rather than sharp teeth. Their jaws are designed to grind rather than slice, allowing them to process a wide range of food. This generalist diet is another key to their survival. When environments fluctuate, specialists struggle. Lungfish remain flexible. If one food source disappears, another often remains. Combined with their ability to slow their metabolism dramatically, this makes lungfish exceptionally resilient. There is temptation to frame lungfish as transitional creatures, halfway between fish and land animals. While they do offer insight into how air breathing evolved, this framing can miss the point. Lungfish are not trying to become something else. They're fully committed to being lungfish. Their anatomy is not incomplete or temporary. It is refined for life at the edge of habitability. Lungs, gills, robust fins, slow metabolism, and tolerance for low oxygen all work together as a single system. This system has worked for an extraordinary length of time. Lungfish survived multiple mass extinctions, including the one that wiped out most marine species at the end of the Devonian period. They endured continental drift, climate shifts, and repeated cycles of drying and flooding. They did so by refusing to commit entirely to either water or land. Instead, they occupy the boundary between the two. In Australia, the lungfish lives in relatively stable rivers and does not estivate, relying on its lungs primarily during low oxygen conditions. In Africa and South America, lungfish face far harsher cycles, and their extreme survival strategies reflect that pressure. This variation shows that lungfish are not frozen in time. Different species adapted differently, fine-tuning the same basic toolkit to local conditions. Their longevity is not due to stubbornness, it is due to adaptability. There's also something quietly unsettling about lungfish survival. While most animals depend on stable ecosystems, lungfish thrive where stability collapses. Drought, heat, stagnation, and decay do not end their story, they trigger it. When conditions worsen, lungfish slow down rather than panic. They retreat rather than fight. They wait rather than flee. This is a very different approach to survival than speed or aggression. It is also extremely effective. Modern lungfish can live for decades. Some individuals kept in captivity have survived for over 50 years. Their slow pace of life extends not just across seasons, but across generations. Breathing air was not a dramatic leap onto land. For lungfish, it was a practical solution to a recurring problem. Water cannot always be trusted. Air usually can. That simple insight carried lungfish through hundreds of millions of years of planetary change. Today, lungfish still surface to breathe, still endure drying rivers, still wait patiently in mud when the world becomes unlivable. They are not relics replaying ancient behaviors. They are living animals, actively navigating extreme conditions using tools that remain as relevant now as they were when forests were new and land was still an experiment. Lungfish did not learn to breathe air in order to leave the water. They learned to breathe air so they could survive when the water left them. The platypus looks like an argument that evolution does not care about neat categories. At first glance, it seems stitched together from unrelated ideas. A flat bill like a duck, dense fur like an otter, webbed feet, a tail built for swimming. It lays eggs. It produces milk. Males carry venomous spurs on their hind legs. Even now, it feels slightly unreal. When the first platypus specimens reached Europe in the late 18th century, some scientists suspected a hoax. The animal looked too contradictory to be genuine. A mammal that laid eggs was already strange enough. Add a bill, webbing and venom, and suspicion felt reasonable. The problem was not the platypus. The problem was expectation. The platypus is a monotreme, part of a small group of mammals that branched off early in mammalian evolution. It does not follow the rules set by placental mammals or marsupials because it diverged before those rules existed. That does not make it incomplete. It makes it independent. The platypus lives in freshwater rivers and streams of eastern Australia, where it spends much of its time foraging underwater. Its body is built for this environment from nose to tail. The bill is not just a beak-like ornament. It is one of the most sophisticated sensory tools found in any mammal. Beneath the smooth surface are thousands of receptors that detect tiny electrical signals produced by muscle contractions in prey. When a shrimp twitches or a worm moves, the platypus senses it instantly. Underwater, vision is unreliable. The platypus closes its eyes, ears, and nostrils while diving. It does not need them. The bill becomes its primary interface with the world, allowing it to hunt by feel and electrical perception combined. This feeding method is precise and efficient. The platypus sweeps its bill back and forth along the riverbed, collecting small invertebrates such as insect larvae, worms, and crustaceans. It stores food in cheek pouches, surfacing periodically to grind it up with tough pads rather than teeth. Adult platypuses do not have teeth. They do not need them. Their limbs tell another part of the story. The webbed front feet act like paddles, providing propulsion through water. On land, the webbing folds back, exposing claws that allow the platypus to dig burrows into riverbanks. These burrows serve as shelter and nesting sites, offering protection from predators and temperature extremes. The tail is broad and flat, storing fat reserves that help sustain the animal during times when food is scarce. It also aids in steering while swimming, adding stability to the platypus's movement. Then there is reproduction. Platypuses lay eggs, a trait shared with only a handful of living mammals. After mating, the female lays 1 or 2 leathery eggs in a secure burrow. She incubates them by curling her body around them, providing warmth and protection until they hatch. Once the young emerge, they do not nurse in the way most mammals do. Platypuses do not have nipples. Instead, milk is secreted through specialized skin glands and pools and grooves on the mother's abdomen. The young lap it up directly. It is a mammalian solution that looks nothing like the standard model, yet accomplishes the same goal. The venomous spur found on male platypuses adds another layer of strangeness. Located on the hind legs, the spur can deliver venom capable of causing intense pain. It is not used for hunting. It is used in competition, particularly during breeding season. The venom is not lethal to humans, but it is potent enough to deter rivals and cause lasting discomfort. This makes the platypus one of the very few venomous mammals, a distinction it did not need, but somehow acquired anyway. All of these traits are not random leftovers. They work together. The The platypus is not confused about what it is. It is highly specialized for a semi-aquatic lifestyle that demands precise sensing, efficient movement, and flexible reproduction. Each odd feature supports that way of life. What makes the platypus especially interesting is that it shows how early mammals experimented. While most mammalian lineages move toward live birth, specialized teeth, and clear separation between sensory systems, monotremes followed a different path. The platypus retained egg-laying, developed novel sensing abilities, and combined traits in ways that feel unconventional only because they are rare today. Rare does not mean wrong. The platypus has survived environmental changes, predators, and competition for millions of years. It did so by carving out a niche that few others could exploit. Its slow metabolism, strong swimming ability, and sensory bill allow it to feed efficiently in murky waters where vision-based hunters struggle. Its burrows offer protection and stability. Its reproductive strategy works well in environments where raising young in hidden locations reduces risk. There is also something quietly charming about the platypus's demeanor. It is not aggressive. It does not dominate its environment. It simply goes about its business, diving, sensing, collecting, resting. The humor comes not from exaggeration, but from the fact that this animal exists at all. The platypus is often described as a patchwork or a puzzle, but that framing misses the elegance of the result. It is not assembled from spare parts. It is assembled from solutions. Each strange trait answers a specific problem: how to hunt without sight, how to move between water and land, how to reproduce safely, how to compete without constant violence. The platypus does not break the rules of biology. It reveals how flexible those rules have always been. In a world that likes clean categories, the platypus refuses to cooperate. It stands as a reminder that evolution is not a straight line toward refinement, but a branching process filled with experiments that worked well enough to last. And the platypus has lasted, not as a curiosity, not as a mistake, but as a living, breathing mammal that simply chose a different way to be one. The naked mole rat lives a life that feels borrowed from another group entirely. It is a mammal, warm-blooded, fur-bearing by ancestry, yet it behaves less like a rodent and more like an insect. Underground, hidden from light, naked mole rats form tightly organized colonies with a single breeding female, a handful of breeding males, and dozens of workers that never reproduce at all. This is eusociality, a social structure most people associate with ants, bees, and termites. In a mammal, it feels almost impossible. Naked mole rats live beneath the dry grasslands of East Africa, where food is scarce, temperatures are stable underground, and survival depends on cooperation. Their tunnels stretch for kilometers, weaving through soil in search of roots and tubers. One colony may occupy a territory larger than a football field, all carved out by small, nearly blind animals working together. Daily life in the colony is divided by role rather than age or gender. Some individuals dig, others transport food, others guard tunnel entrances, a few specialize in caring for the young. These roles are not fixed forever, but the overall structure remains stable. At the center of the colony is the queen. She is not born different, she becomes different. Through social dominance and hormonal control, one female suppresses reproduction in all others. Over time, her body changes. Her spine elongates, allowing her to carry large litters. She produces multiple offspring several times a year, while the rest of the colony remains infertile. This is not enforced by violence alone, it is regulated chemically. Constant social contact maintains the hierarchy. When the queen dies, the system does not collapse. Instead, several females compete, and a new queen emerges. The naked mole rat's body reflects its underground life. It has loose, wrinkled skin that allows it to move easily through tight tunnels. Its eyes are tiny and largely useless. Vision matters little in permanent darkness. Its front teeth protrude outside its mouth, allowing it to dig without filling its lungs with soil. Those teeth are powerful enough to excavate hard ground and cut through thick plant roots, which serve as the colony's main food source. One large tuber can sustain dozens of animals for weeks, eaten slowly so the plant can regrow. Efficiency matters more than abundance. Perhaps the most unsettling feature of naked mole rats is their tolerance for conditions that would kill most mammals. They thrive in low oxygen environments. In crowded tunnels, carbon dioxide levels can rise sharply. Naked mole rats respond by slowing their metabolism rather than panicking. In extreme cases, they can switch to a form of anaerobic metabolism, using sugars in a way similar to plants. This allows their cells to survive without oxygen for extended periods, a feat unheard of in most mammals. Their bodies also handle pain differently. Naked mole rats lack certain neurotransmitters involved in transmitting pain signals from the skin. Acidic environments, such as high carbon dioxide air, do not cause the same burning sensation they would in other animals. In the tunnels, this is not a curiosity. It is a necessity. Longevity is another surprise. Despite their small size, naked mole rats can live for over 30 years, far longer than most rodents. They show little sign of aging for much of that time. Cancer is extremely rare among them, and their cells exhibit unique protective mechanisms that prevent uncontrolled growth. This longevity makes sense in context. In a eusocial system, individuals invest less in reproduction and more in maintenance. When survival of the group matters more than individual turnover, long life becomes advantageous. The naked mole rat's biology reflects this shift. Their social behavior reinforces it. Individuals rarely leave the colony. Dispersal is risky and uncommon. Safety comes from numbers, from shared labor, from tunnels that buffer the outside world. Predators are avoided not through speed or aggression, but by staying hidden. Above ground, naked mole rats are awkward and vulnerable. Below ground, they are perfectly at home. This lifestyle challenges deeply held assumptions about mammals. Mammals are supposed to be independent breeders. They are supposed to compete for mates. They are supposed to live in small family groups, not superorganisms. Naked mole rats ignore all of that. They show that mammalian behavior is more flexible than expected. Under the right conditions, cooperation can replace competition. Reproductive sacrifice can become the norm rather than the exception. Importantly, naked mole rats are not confused or stressed by this arrangement. Their brains and hormones are tuned to it. Workers do not appear to experience frustration at their lack of reproduction. Their role is not temporary, it is their life. Eusociality in naked mole rats is not a failed mammal experiment. It is a successful response to a harsh environment where survival alone is difficult and raising young alone is even harder. By sharing the burden, the colony persists. There's also something quietly humorous about the contrast. An animal that looks fragile, hairless, and almost unfinished has developed one of the most complex social systems among mammals. Under the soil, naked mole rats live in a world of order, routine, and collective purpose. They may not win beauty contests. They may not inspire admiration at first glance, but they represent one of the clearest examples of how deeply environment can shape not just bodies, but societies. The naked mole rat lives like an insect because in its world that is what works, and by every evolutionary measure that matters it works remarkably well. The eye feeds in a way that looks more like a magic trick than a meal. Found only on the island of Madagascar, the eye is a nocturnal primate that spends its nights moving quietly through trees, listening more than looking. Its large eyes help in the dark, but its most important tool is not its vision. It is its finger. The eye's middle finger is long, thin and skeletal, far more delicate than the others. It bends in strange ways, moving independently, tapping rapidly against wood like a metronome. At first glance, it looks fragile, even unsettling. In practice, it is one of the most specialized feeding tools in the primate world. The eye uses a method known as percussive foraging. As it moves along branches, it taps its finger against the bark, listening closely to the sound that comes back. Hollow spaces sound different from solid wood. Cavities filled with insect larvae produce subtle acoustic cues that the eye's ears are finely tuned to detect. When it hears the right sound, the eye switches tools. Its front teeth, which grow continuously like those of a rodent, are used to gnaw through bark and wood. Unlike most primates, whose teeth are suited for fruit and leaves, the eye's incisors are strong enough to carve open trees. Once the hole is made, the skeletal finger slips inside. It hooks, probes, and extracts grubs hidden deep within the wood. The finger is thin enough to reach into tight spaces, flexible enough to maneuver, and fast enough to pull prey out before it can retreat. This feeding strategy allows the eye to exploit a food source that few other animals can access. Wood-boring insects are abundant, nutritious, and largely uncontested. While other primates compete for fruit and leaves, the eye feeds where competition is minimal. Its strange anatomy makes sense when viewed through this lens. The finger is not grotesque, it is precise. The teeth are not excessive, they are necessary. Even the eye's large ears play a role, amplifying faint sounds produced by movement inside wood. Each feature supports the same behavior, forming a tightly integrated system built around feeding. This specialization shapes the eye's entire life. Eyes are solitary animals moving alone through large territories. Their feeding method is slow and methodical, tapping, listening, gnawing, extracting, repeating the process again and again through the night. There is no need for speed or group coordination. Success comes from patience. Their diet is not limited to insects. Eyes also eat fruit, seeds, nectar, and fungi, using the same finger to scoop soft food or pry open tough shells. This flexibility helps them survive seasonal changes when insect availability fluctuates. Still, it is the finger that defines them. That finger has also shaped how humans perceive the eye, often unfairly. In some local traditions, the eye is considered an omen of bad luck or misfortune. Its nocturnal habits, strange appearance, and piercing eyes have made it a target of fear and superstition. This has had real consequences. Habitat loss and persecution have reduced eye populations in many regions. Forest destruction removes not just shelter, but the specific trees and insect communities the eye depends on. Because their feeding strategy is so specialized, they cannot easily switch habitats. Yet where conditions remain suitable, eyes persist. They're intelligent, curious animals. Observations show them exploring objects, solving simple problems, and adapting their behavior based on experience. Their feeding technique is learned and refined over time, not purely instinctive. Young eyes watch and practice. Skill matters. There's also something quietly elegant about how the eye feeds. It does not overpower its environment. It listens to it. It reads sound, texture, and resistance, turning subtle cues into nourishment. In evolutionary terms, the eye represents a primate that took an unusual route. Rather than competing directly with other lemurs for fruit and leaves, it carved out a niche that required anatomical boldness. That boldness came with risk. Specialization can be dangerous if conditions change, but as long as forests stand and insects burrow into wood, the eye's approach works extremely well. The skeletal finger is not a flaw or an oddity. It is the center of the eye's survival strategy, shaping how it feeds, where it lives, and how it moves through the night. Seen in motion, tapping softly against bark, pausing, listening, then acting with precision, the eye feels less like a curiosity and more like a specialist doing exactly what it evolved to do. It survives not by force or speed, but by turning sound into food. In the dark forests of Madagascar, that strange finger is not unsettling at all. It is essential. The barrel-leaf fish looks like it was designed to break trust. At first glance, its face appears blank, almost unfinished. A small mouth, no obvious eyes, just a smooth, rounded dome where a head should be. For a long time, this made the barrel-leaf difficult to understand and even harder to believe. Then scientists realized the head was transparent. Living in the deep ocean, usually at depths of several hundred meters, the barrel-leaf fish inhabits a world of perpetual twilight. Sunlight is weak, shadows are soft, food is scarce and often bioluminescent. In this environment, seeing clearly is everything. The barrel-leaf solved that problem in an extraordinary way. Inside its transparent head are two large barrel-shaped eyes, normally pointed straight upward. These eyes are not fixed. They can rotate, allowing the fish to look forward when needed, but most of the time they stare directly toward the surface. That orientation makes sense. In the deep sea, many animals glow. Small crustaceans, jellyfish, and drifting organisms often produce faint light from above. By looking upward, the barrel-leaf can spot silhouettes and glimmers against the dim background, detecting prey that would otherwise be invisible. The transparent head acts like a natural window. Rather than placing eyes on the outside, where they would be exposed and limited by surrounding tissue, the barrel-leaf encloses them inside a fluid-filled dome. This reduces distortion and protects the delicate structures while still allowing light to pass through. The eyes themselves are highly specialized. They contain green pigments that filter out certain wavelengths of light, improving contrast in the blue-dominated deep-sea environment. This fine-tuning allows the barrel-leaf to distinguish prey from background glow with remarkable sensitivity. For a fish that feeds on small drifting organisms, this advantage is enormous. Barrel-leaf fish feed primarily on zooplankton and small animals suspended in the water column. Some of this prey lives among the tentacles of jellyfish, where it is partially protected. The barrel-leaf's upward gaze helps it locate food without triggering defensive stings, approaching carefully from below or the side. Its mouth, though small, is well suited for plucking soft-bodied prey. Feeding is slow and deliberate. There is no chasing, no sudden lunges. Energy is conserved at all times. That conservation is essential in the deep sea. Movement is minimal. The barrel-leaf drifts quietly, hovering with subtle fin motions. Every action is measured. Wasted effort cannot be replaced easily when meals are unpredictable. The fish's body supports this lifestyle. It is small, slender, and lightly built. There is no heavy armor, no unnecessary muscle mass. Buoyancy is carefully balanced, allowing it to remain suspended without constant swimming. The transparent head also offers protection. In the deep ocean, anything reflective or protruding can attract attention. By enclosing its eyes inside a smooth dome, the barrel-leaf reduces exposed surfaces and potential damage. Predators find little to grab, and delicate tissues stay shielded from accidental contact. For decades, illustrations of the barrel were wrong. Early depictions showed eyes fixed at the front of the face because scientists did not realize the head was clear. It was only with advances in deep-sea imaging that the truth became visible. Seeing a living barrel for the first time was unsettling even to experts. The eyes rolled inside the skull, the head gleamed faintly. It looked less like a fish and more like a living observation chamber. But there is nothing accidental about its design. Every strange feature serves the same purpose: see faint light, detect prey, avoid harm, use as little energy as possible. The barrel fish is not weird for the sake of being weird. It is precise. In the deep ocean, evolution favors solutions that feel counterintuitive on land. Transparency becomes protection. Looking upward becomes survival. Hiding eyes inside the head becomes sensible. The barrel shows how far anatomy can be pushed when environments demand it. It also reminds us that unfamiliar does not mean impractical. In its world, the barrel is not strange at all. It is well adapted, quietly efficient, and perfectly tuned to a place where light is rare and mistakes are costly. Drifting in darkness, eyes pointed skyward behind a clear dome, the barrel fish watches a faint glow pass overhead and decides whether it is worth the effort. Most of the time, it waits, and in the deep sea that patience is exactly what keeps it alive. The anglerfish lives where light does not belong. Far below the ocean surface, sunlight fades into darkness so complete that vision becomes unreliable, and movement becomes expensive. Food drifts sparsely through the water. Encounters are rare. In this world, chasing prey is inefficient. Waiting is smarter. The anglerfish solved this problem by bringing its own light. Anglerfish are a group of deep-sea fish found at great depths, often more than a kilometer below the surface. Their bodies are soft and expandable, their bones light, their movements slow and deliberate. Everything about them reflects an environment where energy must be conserved and opportunity arrives unpredictably. The most famous feature of the anglerfish is the lure. Extending from the top of the head is a modified spine tipped with a glowing bulb. This structure is not decorative, it is a tool. Inside the bulb live bioluminescent bacteria that produce light through chemical reactions. The fish does not generate the light itself, it maintains a living lantern. In the deep sea, light attracts attention. Small fish and invertebrates are drawn to glows in the darkness, mistaking them for food, mates, or signals. The anglerfish positions its lure just in front of its mouth and waits. When something approaches closely enough, the fish opens its jaws and the encounter ends. There is no chase, no pursuit, just patience and timing. The anglerfish's mouth is perfectly suited to this strategy. It is enormous relative to the body, lined with long inward-pointing teeth. The jaws can open wide enough to swallow prey, nearly as large as the anglerfish itself. The stomach stretches to accommodate meals that arrive rarely, but must last a long time. This ability to eat large prey is essential. In the deep sea, meals are unpredictable. When food appears, it must be used fully. Anglerfish do not waste opportunities. Their bodies are not built for speed or endurance. Muscles are reduced. Fins are used for subtle positioning rather than propulsion. Drifting is common. Movement is minimal. Energy is spent only when necessary. Bioluminescence makes this strategy possible. Without the lure, the anglerfish would be forced to roam, searching blindly in darkness. That would be inefficient and risky. By using light as bait, the fish reverses the usual predator-prey relationship. Prey comes to it. The light itself can be controlled. Anglerfish can vary the brightness and movement of the lure, creating subtle motions that mimic living organisms. Some species have multiple glowing points. Others have elongated filaments. Each variation reflects the specific environment and prey types encountered. The lure is not the only strange feature. In many deep-sea anglerfish species, males and females live very different lives. Females are much larger and carry the lure. Males are tiny by comparison, sometimes little more than a pair of nostrils and reproductive organs attached to a small body. When a male encounters a female, he bites onto her body and does not let go. Over time, the male fuses with the female's tissues. His circulatory system connects to hers. He loses his eyes, his digestive system, and his independence. He becomes a permanent source of sperm, living off the female's blood supply. This sounds extreme, but it solves a deep-sea problem. Finding a mate in the vast darkness of the deep ocean is incredibly difficult. Encounters are rare. By permanently attaching, the male ensures that when the female is ready to reproduce, fertilization is guaranteed. This reproductive strategy reflects the same principle as the anglerfish's hunting style. When opportunity is rare, do not let it go. The female, meanwhile, continues her life largely unchanged. She hunts, feeds, and drifts through darkness with her glowing lure, carrying her mate with her as a biological certainty rather than a temporary partner. Anglerfish anatomy supports this life of waiting. Their skin is often dark or mottled, blending into the surrounding water. Some species have loose, sagging bodies that reduce outlines and reflections. Predators that rely on vision struggle to distinguish the fish from the background. The eyes are functional but not dominant. Senses such as smell and lateral line detection play important roles in detecting movement and changes in water pressure. But the primary interface with the environment remains the lure. Light becomes language. It signals, it tempts, it deceives. Bioluminescence in the deep sea is common, but the anglerfish uses it differently. Many animals glow to confuse predators or communicate with their own kind. The anglerfish uses light as a weapon, turning curiosity into vulnerability. There is something unsettling about this, but it is also efficient. Anglerfish do not need to be fast. They do not need to be strong. They need only to be convincing. And they are. The glow is not constant. It flickers, it pulses, it moves slightly, mimicking the behavior of small living creatures. In darkness, that is enough. Anglerfish also illustrate how deep-sea life pushes anatomy to extremes. When environments remove familiar constraints, evolution explores solutions that would seem impossible elsewhere. On land, glowing organs would attract predators. In shallow water, they would be overwhelmed by sunlight. In the deep ocean, they become tools of precision. The anglerfish does not dominate its environment by force. It controls attention. It waits in silence, barely moving, while the light does the work. When the moment arrives, the action is swift, final, and efficient. There is no drama, no struggle, just the sudden absence of a glow where something once hovered. Anglerfish remind us that predation does not always look like pursuit. Sometimes it looks like stillness. They also show how deeply life can adapt to absence. In a place without light, the anglerfish manufactures it. In a place without frequent encounters, it commits permanently. In a place where energy is scarce, it spends almost none. Everything about the anglerfish is tuned to its world. It does not resemble animals from brighter places because it does not live by their rules. It lives where patience matters more than speed, where attraction replaces pursuit, and where survival depends on turning the environment's limits into advantages. In the deep sea, the anglerfish waits. A faint glow drifts in the darkness. Something notices, and that is enough. The giant isopod looks like a familiar creature scaled far beyond comfort. It resembles the small pill bugs that hide under rocks in gardens, except stretched to the length of a forearm, armoured, pale, and slow-moving. The resemblance is not accidental. Giant isopods are crustaceans, relatives of shrimp, crabs, and those tiny land-dwelling isopods people casually ignore. In the deep sea, that basic design grew enormous. Giant isopods live hundreds to thousands of meters below the ocean surface, where darkness is constant, pressure is immense, and food is unpredictable. In this environment, size itself becomes a strategy. Some species of giant isopod can reach lengths of nearly half a meter and weigh several kilograms. That makes them among the largest isopods ever known, dwarfing their shallow water and terrestrial relatives. Their bodies are flattened and segmented, protected by thick, overlapping plates that form a flexible but robust armor. This shell is not decorative. It shields the animal from pressure, predators, and accidental damage as it moves across the seafloor. The pale coloration reflects their world. In perpetual darkness, pigment serves little purpose. Energy is better spent elsewhere. Giant isopods move slowly, using jointed legs to walk along the ocean bottom. They do not swim long distances. They patrol, investigate, and wait. Speed would waste energy in a place where calories arrive rarely. That rarity shapes everything about them. Food in the deep sea does not fall evenly. Long stretches of scarcity are interrupted by sudden abundance. A dead whale, a large fish carcass, or a cluster of sinking organic matter can provide a massive but temporary feast. Giant isopods are built to take advantage of these moments. They're opportunistic scavengers, capable of detecting food from a distance using chemical cues. When they find a carcass, they gather and feed intensively, consuming enormous quantities relative to their normal intake. Their digestive systems are adapted for this boom and bust lifestyle. Giant isopods can gorge themselves until their bodies visibly swell, then survive for months or even years without another meal. Some individuals in captivity have gone for several years without eating and remained healthy. Size supports this endurance. A larger body stores more energy, loses heat slowly, and tolerates starvation better than a smaller one. In the deep sea, where metabolism is slow and food unpredictable, being large reduces risk. Their metabolism reflects this strategy. Giant isopods operate at a low baseline energy level. Movements are deliberate. Reactions are unhurried. There is no rush when waiting is safer. The legs beneath their armoured bodies are strong but not built for speed. Each step is controlled. Their antennae probe the environment, sampling chemical signals and vibrations in the water. When threatened, giant isopods can curl slightly, using their armour as protection. While they are not aggressive predators, their size and shell make them an unappealing target. Few deep-sea animals are eager to attack something so well protected and nutritionally uncertain. Reproduction also follows the deep-sea rhythm. Giant isopods reproduce slowly. Females brood their eggs in a pouch beneath the body, protecting developing young rather than releasing them into the open water. This increases survival rates in an environment where random dispersal would likely mean death. The young emerge as miniature versions of adults, already armoured and capable of surviving on the seafloor. There is no larval stage drifting helplessly in the water column. Again, reliability over quantity. Giant isopods were first discovered in the late 19th century, when deep-sea exploration revealed animals that seemed to violate expectations. Until then, it was widely believed that deep ocean life was sparse and small. Giant isopods helped overturn that idea. They showed that the deep sea does not always produce miniaturized creatures. Under the right conditions, it can do the opposite. This phenomenon is known as deep-sea gigantism, where some animals grow larger than their shallow water relatives. Several factors contribute to this trend. Cold temperatures slow metabolism. Stable environments reduce the need for rapid reproduction. Scarce food favors energy storage and endurance. Together, these pressures reward size. The giant isopod embodies this logic perfectly. It is not large because it is aggressive or dominant. It is large because size solves problems in its world. It buffers against starvation. It discourages predation. It stabilizes physiology in an extreme environment. There is something quietly unsettling about encountering a giant isopod. Its movements are calm. Its face, if it can be called that, is unreadable. It does not flee or charge. It simply exists, armored and patient, doing exactly what it evolved to do. Despite their intimidating appearance, giant isopods are not monsters. They do not attack humans. They do not hunt living animals aggressively. They are recyclers, breaking down the remains of life that sinks into the deep. In doing so, they play an important ecological role. Without scavengers like giant isopods, the deep sea would accumulate vast amounts of organic debris, disrupting nutrient cycles. Their slow, methodical feeding helps return material back into the system. Giant isopods remind us that size does not always signal dominance in the dramatic sense. Sometimes it signals resilience. They also show how evolution stretches familiar forms into unfamiliar extremes when conditions demand it. A body plan that works on land under rocks can, given enough time and the right pressures, become something that patrols the ocean floor in darkness. The giant isopod is not a mistake or an exaggeration. It is a scaled solution. In a world where food arrives rarely, danger is constant, and light never comes, growing large is not excess. It is insurance. And so the giant isopod moves slowly across the seafloor, armored, patient, and enduring, carrying a familiar shape into an unfamiliar depth, and proving that sometimes survival simply means becoming big enough to wait. The vampire squid suffers from an unfortunate name. It is not a vampire, and it is not really a squid. It does not drink blood, does not hunt aggressively, and does not behave like the fast, muscular squids people usually imagine. Instead, it lives quietly in one of the most extreme environments in the ocean, surviving by doing almost the opposite of what most deep-sea animals do. The vampire squid is its own thing. It lives in the deep ocean, typically at depths between 600 and 900 meters, within regions known as oxygen minimum zones. These are areas where oxygen levels are so low that many animals cannot survive for long. For most creatures, this zone is a barrier. For the vampire squid, it is home. Its body reflects this unusual choice. The vampire squid is small, soft-bodied, and slow-moving. It has large eyes relative to its size, adapted to collect as much faint light as possible. Its coloration is dark red to black, a clever form of camouflage in deep water where red light does not penetrate. To predators, red appears invisible. Despite the name, the vampire squid does not chase prey. It does not need to. Instead of hunting living animals, the vampire squid feeds on what marine biologists call marine snow. This is a constant drizzle of organic debris sinking from above, made up of dead plankton, fecal pellets, shed shells, and other fragments of life. It is not glamorous food, but it is reliable. The vampire squid drifts with its arms extended, collecting this material using sticky filaments and webbing between its limbs. Mucus helps trap particles, which are then rolled into small food packages and consumed. This feeding strategy is slow but extremely efficient. Marine snow is abundant in oxygen minimum zones because fewer animals are there to compete for it. While predators avoid these regions due to low oxygen, the vampire squid thrives by taking advantage of what others ignore. Its metabolism makes this possible. The vampire squid has one of the lowest metabolic rates ever measured in a cephalopod. It uses very little energy, moves infrequently, and can tolerate oxygen levels that would suffocate most animals. Its blood binds oxygen extremely efficiently, allowing it to extract what little is available from the surrounding water. This is not an animal built for speed or power. It is built for endurance. The vampire squid's arms are another source of confusion. It has 8 arms connected by a web of skin, giving it a cloak-like appearance. When threatened, it can wrap this cloak around its body in a defensive posture, exposing spines and dark surfaces while hiding vulnerable parts. This display looks dramatic, but it is largely a bluff. The vampire squid is not heavily armed. It relies on avoiding attention rather than fighting. Its movements are slow and deliberate, minimizing disturbances in the water that might attract predators. If that fails, it has one more trick. The vampire squid can release clouds of bioluminescent mucus from the tips of its arms. These glowing particles stick together and linger in the water, confusing predators and drawing attention away from the animal itself. Unlike ink used by other cephalopods, this mucus does not create a dark cloud. It creates light. In the deep sea, light can be more distracting than darkness. The name vampire squid comes partly from its dark coloration and webbed arms, which resemble a cloak. It also comes from small spines along its arms that look like teeth. These spines are not used for feeding or combat. They are simply part of its defensive display. There's no blood drinking, no aggression, no lurking attacks. What makes the vampire squid especially fascinating is its evolutionary position. It is not closely related to modern squids or octopuses. Instead, it belongs to an ancient lineage that split off early in cephalopod evolution. In many ways, it represents a surviving branch of a much older experiment. That experiment was not about speed, intelligence, or dominance. It was about persistence. The vampire squid occupies a niche that few animals can tolerate. Low oxygen, low energy, low competition. By slowing everything down and feeding on what drifts past, it avoids the constant arms race that defines much of ocean life. It does not need sharp beaks or powerful tentacles. It does not need to chase or ambush. It simply needs to exist efficiently in a place others cannot. There is a tendency to describe animals like the vampire squid as strange leftovers, as if they fail to keep up with more successful relatives. This interpretation misses the point. The vampire squid is not behind. It is elsewhere. Its strategy would not work in shallow, well-oxygenated waters filled with fast predators. It will be outcompeted instantly. But in the oxygen minimum zone, it faces little pressure to change. That stability allows its unusual traits to persist. Even its slow movement becomes an advantage. Sudden motion would waste energy and draw attention. Stillness keeps it alive. The vampire squid shows that evolution does not always reward complexity or aggression. Sometimes it rewards restraint. By feeding on marine snow, it recycles nutrients that would otherwise sink unused. By occupying oxygen-poor zones, it expands the range of environments where life can function. It plays a quiet but important role in deep ocean ecosystems. There is nothing theatrical about how the vampire squid lives. It drifts, it collects, it conserves. In a deep sea where survival often depends on speed or strength, the vampire squid chose patience instead. It is neither squid nor vampire. It is not a hunter, not a terror, not a relic waiting to vanish. It is a carefully tuned solution to a difficult problem. And in the low oxygen darkness where most animals struggle, the vampire squid continues to float, gather falling fragments of life, and prove that sometimes the strangest strategy is simply to slow down enough for the world to come to you. The Portuguese man-o'-war looks like a single drifting creature. A translucent blue float catches the sunlight. Long, trailing tentacles hang beneath the surface. It moves with the wind, riding waves across warm oceans, seemingly simple and self-contained. But that impression is wrong. The Portuguese man-o'-war is not one animal in the usual sense. It is a colony, a living alliance of many individual organisms fused together so completely that they function as one, and none of them could survive alone. Each Portuguese man-o'-war begins life as a tiny larva. Through development, that larva does not grow into a single body. Instead, it buds repeatedly, producing genetically identical individuals called zooids. Each zooid specializes in one task, and once assigned, it never changes roles. There is no redundancy, there is no independence, there is only cooperation. One zooid becomes the float, the gas-filled structure that keeps the colony at the surface. This float, often mistaken for a jellyfish bell, acts as a sail. It catches the wind and determines where the colony drifts. It cannot feed, it cannot sting, it exists solely to keep the rest of the colony afloat. Other zooids become feeders. They handle digestion, breaking down captured prey and distributing nutrients throughout the colony. Without them, nothing eats. Then there are the hunters. The long tentacles trailing beneath the float are made up of zooids specialized for capturing prey. These tentacles can extend for tens of meters, armed with microscopic stinging cells that inject venom on contact. Fish, crustaceans, and other small animals that brush against them are paralyzed almost instantly. Once prey is immobilized, it is hauled upward to the feeding zooids, which begin digestion. Nutrients are shared through a common internal network, sustaining every part of the colony. There are also reproductive zooids, responsible only for producing the next generation. They never hunt, they never feed, they exist to continue the lineage. Together these zooids form something that behaves like an animal, even though no single part qualifies as one on its own. The Portuguese man-o'-war cannot swim, it cannot steer precisely, it drifts where wind and currents take it. This might sound like a disadvantage, but it is part of the strategy. By drifting, the colony covers vast distances without spending energy. It encounters new feeding grounds continuously. The ocean does the work. Its sail can even be oriented slightly left or right, creating different drift patterns. Some individuals are biased to one direction, others the opposite. This reduces the chance that entire populations wash ashore at once. Survival through variation. The venom of the Portuguese man-o'-war is potent. It is designed to stop fast-moving prey immediately. For humans, contact is painful and sometimes dangerous, but humans are not the target. The venom evolved to capture fish in open water, where hesitation means escape. Despite its fearsome reputation, the Portuguese man-o'-war is not aggressive. It does not pursue. It does not attack deliberately. Its stings are defensive side effects of feeding structures that cannot distinguish between prey and accident. Once prey is captured, the colony feeds slowly. Digestion takes time. There is no rush. Drifting continues while the internal systems process the meal. Predators do exist. Some animals have learned to exploit the man-o'-war despite its venom. Certain fish and sea slugs can feed on its tentacles without harm, stealing both food and stinging cells. Sea turtles are known to consume man-o'-wars whole, largely unaffected by the venom. Even here, the colony persists through numbers rather than defense. The Portuguese man-o'-war's life cycle is tied closely to ocean conditions. Warm waters, steady winds, and surface productivity all shape where it thrives. When conditions align, populations bloom. When they shift, colonies disappear from view, drifting elsewhere rather than dying off entirely. This mobility makes them difficult to track and easy to misunderstand. They are often mistaken for jellyfish, but they are not closely related. Jellyfish are single organisms with multiple tissues performing all functions. The Portuguese man-o'-war distributes those functions across separate individuals. It is not a single body with many organs. It is many bodies behaving as one. This raises a deeper question about what an animal actually is. The Portuguese man-o'-war has no brain, no central control, no leader. Coordination emerges from structure rather than command. Each zooid performs its task automatically, responding to local signals and shared circulation. Together they create something that feeds, moves, reproduces, and survives. Remove one essential zooid type, and the entire colony fails. This extreme interdependence is not fragile. It has worked for millions of years. In open ocean environments where encounters are unpredictable and energy must be conserved, dividing labor makes sense. Specialization increases efficiency. Drift replaces movement. Venom replaces pursuit. The result is an organism that feels alien not because it is dangerous, but because it challenges intuition. There is no clear front or back, no single mouth or stomach, no individual that can be pointed to and called the animal. And yet, the Portuguese man-o'-war behaves like one. It drifts across oceans, feeds, reproduces, and persists carried by wind, bound together by necessity, and shaped by a world where cooperation is not a choice but a requirement. Seen from a distance, it is a delicate blue float gliding across waves. Seen more closely, it is a society, a living agreement between many organisms to stop being individuals and start being something larger. The Portuguese man-o'-war is not a swarm, it is not a collection, it is not a mistake. It is a single name given to many lives moving together, proving that sometimes survival does not come from becoming stronger alone, but from becoming inseparable. A siphonophore does not fit comfortably into the idea of a single body. At first encounter, it looks like a delicate chain drifting through open water, glowing faintly, stretching far beyond what seems reasonable for an animal. Some siphonophores measure longer than a blue whale. Others extend for tens of meters, disappearing into darkness before the eye can find an end. Yet despite that length, a siphonophore is not a giant creature in the usual sense. It is many creatures, bound together so tightly that they behave as one. Like the Portuguese man-o'-war, siphonophores are colonial animals. But where the man-o'-war spreads out at the surface, siphonophores descend into the deep, building bodies that are vertical, elongated, and modular. Each individual unit is called a zooid, and each zooid performs a specific role. None can survive alone. The siphonophore begins life as a single larva. From that point on, growth does not mean getting bigger in the familiar way. Instead, the larva buds repeatedly, producing new zooids that attach in a precise sequence. The order matters, the spacing matters, the final structure is not random, it is assembled. Some zooids become floats, filled with gas that controls buoyancy. These allow the siphonophore to adjust its position in the water column, rising or sinking with subtle changes. Others become swimmers, contracting rhythmically to propel the entire colony forward. Still others become feeders, digesting captured prey and distributing nutrients throughout the shared internal system. And then there are the hunters. The hunting zooids carry long tentacles armed with stinging cells. These tentacles trail behind the colony like fine threads, forming an enormous capture net. Small fish and crustaceans that drift into this invisible field are stunned and pulled inward, delivered to the feeding zooids. The result is an animal that hunts without chasing. It drifts, stretches, and waits. The length of a siphonophore is not decorative. It increases the chances of encounter. In open ocean environments, prey is sparse and widely distributed. By extending its reach, the siphonophore increases the area it samples without increasing energy expenditure. Modularity makes this possible. If part of the colony is damaged, the rest continues functioning. If a zooid fails, it does not doom the entire organism immediately. Redundancy is built into the structure. Growth can continue at one end while feeding occurs elsewhere. There is no single vital organ whose failure means instant death. Control in a siphonophore is decentralized. There is no brain issuing commands. Coordination arises through local signals, rhythmic contractions, and shared circulation. Zooids respond to chemical and mechanical cues, adjusting their behavior automatically. This produces movement that looks purposeful, even though no single part is in charge. In the deep sea, this matters. Siphonophores inhabit mid-water zones where light is minimal and landmarks do not exist. Precision navigation is less important than persistence. By maintaining shape, orientation, and slow forward motion, the colony sweeps through space efficiently. Many siphonophores are bioluminescent. Some glow faintly along their length. Others produce sudden flashes when disturbed. These lights may help confuse predators, startle attackers, or attract prey toward the tentacles. Light becomes another distributed tool, not centralized in one organ, but repeated across many units. The appearance of a siphonophore can be mesmerizing. Transparent bodies refract light. Tentacles shimmer. Patterns repeat again and again along the chain. It feels more like a structure than a creature. And yet it feeds, grows, and reproduces. Reproduction in siphonophores adds another layer of complexity. Some zooids specialize solely in producing reproductive cells. When the time comes, these zooids release eggs or sperm into the water. The colony itself does not split or give birth. It delegates reproduction to specific members. The next generation begins again as a single organism, which then builds itself into a colony. This raises an unsettling question. Where does the animal actually exist? Is it the entire chain? Is it the individual zooids? Is it the pattern that holds them together? Biologically, the answer is the whole. Evolution treats the siphonophore as one unit. Natural selection acts on the success of the colony, not on the fate of individual zooids. This perspective explains why siphonophores can grow so large. There is no requirement to maintain symmetry or compactness. Length is not a liability when control is distributed and movement is slow. In fact, length becomes an advantage. Some siphonophores are believed to be the longest animals ever observed, exceeding any whale, snake, or worm. They achieve this not by growing bigger parts, but by adding more parts. The design scales. That scalability is what makes siphonophores such powerful examples of modular life. Instead of building complexity by refining organs, they build it by repeating them. Each zooid is relatively simple. Together they form something vast. This approach has endured for millions of years. Siphonophores have existed since ancient oceans, refining their colonial strategies while many solitary lineages vanished. Their success lies not in speed or strength, but in architecture. They turn the ocean itself into a feeding space. There was also something quietly humbling about encountering a siphonophore. Divers describe seeing what looks like a faint, endless ribbon suspended in darkness, only realizing its scale as it continues far beyond visibility. It does not flee, it does not attack, it simply occupies space. In a world where survival often depends on reaction time, the siphonophore survives by being present everywhere it needs to be, all at once. The siphonophore challenges the idea that animals must be compact, centralized, or even clearly bounded. It shows that life can be stretched, distributed, and assembled in ways that feel architectural rather than anatomical. It is not a swarm. It is not a colony pretending to be an individual. It is a single evolutionary solution built from many repeating lives, drifting through dark water, extending tentacles into empty space. The siphonophore continues to grow by addition rather than transformation, proving that sometimes the strangest animals are not defined by what they look like, but by how they are put together. In the open ocean, where boundaries blur and scale loses meaning, the siphonophore does not ask how big an animal should be. It simply keeps adding itself until the answer is long enough. Some siphonophores do not just drift, they stretch. Far beyond what feels reasonable for an animal, giant siphonophores extend through open water as long, delicate chains, sometimes measuring tens of meters from end to end. Encountered in the deep ocean, they do not announce themselves with bulk or speed. They reveal themselves slowly, section by section, until it becomes clear that what looked like a stray filament is an animal with no obvious beginning or end. These giant siphonophores are not abstractions or theoretical constructs. They are living animals, moving, feeding, and responding to their surroundings in real time. Their size is not an accident. It is the direct result of how they are built. A giant siphonophore begins life as a single individual. From that point on, it grows not by enlarging organs, but by adding new ones. Each added unit is a zooid, genetically identical to the rest, but permanently specialized. Some pulse to move the body, some capture prey, some digest food, some manage buoyancy. None can survive on its own. Together, they form one animal. In giant species, this process continues far longer than in smaller relatives. New zooids keep forming at the growth end, extending the body into a structure that can exceed the length of any vertebrate. Yet despite this scale, the siphonophore does not become clumsy or slow to respond. This is where distributed control becomes essential. There is no brain at the center of a giant siphonophore, no command hub deciding when to move, feed, or react. Instead, control is local. Each zooid responds to chemical signals, pressure changes, and electrical cues in its immediate surroundings. These responses propagate along the colony, producing coordinated behavior without centralized planning. Movement emerges from rhythm. Swimming zooids contract in waves, pushing water backward and gently propelling the entire animal forward. The timing does not require a conductor. It arises from feedback between neighboring units. If one section encounters resistance, nearby sections adjust automatically. This allows the siphonophore to remain coherent even as it stretches across currents with different speeds and directions. Feeding works the same way. The hunting zooids carry tentacles that trail behind the animal, forming an enormous capture field. When prey contacts a tentacle, stinging cells fire locally. The signal to contract and draw the prey inward spreads along the tentacle and into the feeding zooids nearby. Digestion begins without requiring the rest of the colony to pause or redirect. One part eats while another grows, another moves, another reproduces. All of it happens at once. In giant siphonophore species, this distributed approach becomes even more important. A body that long cannot rely on rapid signals traveling from one end to the other. Instead, the animal functions more like a responsive landscape than a single reacting object. This does not make it passive. Giant siphonophores adjust their depth using gas-filled floats that change volume subtly, allowing the animal to rise or sink in the water column. This positioning is crucial. Too shallow, and predators increase. Too deep, and prey becomes scarce. The animal does not calculate this consciously. Individual buoyancy zooids respond to pressure and chemistry, altering gas content in small increments. The combined effect moves the entire animal. Light also plays a role. Many giant siphonophores are bioluminescent. Some glow continuously along sections of their bodies. Others produce sudden flashes in response to disturbance. These lights are not decorative. They can startle predators, attract prey, or redirect attention away from vulnerable sections. Because the light is distributed, damage to one glowing area does not eliminate the function. Other sections continue producing light. This redundancy is critical. Giant siphonophores live in environments where encounters with debris, predators, and currents are unavoidable. Losing a section is not catastrophic. The rest of the animal continues operating, and growth can replace what was lost. This ability to absorb damage without total failure is one of the reasons such animals can afford to be long. Predators face a dilemma. Attacking a giant siphonophore rarely delivers a decisive outcome. There is no obvious vital organ to destroy. Biting off a section may injure the animal, but it does not end it. For many predators, the energy cost outweighs the reward. As a result, giant siphonophores exist in a space between prey and structure, neither easily eaten nor aggressively defended. Their feeding strategy benefits from this. By extending long tentacles through the water, giant siphonophores sample a huge volume of space with minimal effort. Prey density in the open ocean is low. Length compensates for scarcity. Instead of moving to find food, they let food encounter them. This is not randomness. The arrangement of tentacles follows precise spacing patterns that maximize encounter rates while minimizing tangling. Zooids form in specific sequences that preserve function as length increases. Growth without chaos, reproduction adds another layer. In many giant siphonophores, specific zooids are dedicated solely to producing eggs or sperm. When the time is right, these zooids release reproductive cells into the water. The animal itself does not divide or fragment to reproduce. It delegates reproduction while maintaining structural integrity. The offspring begin as single organisms, not colonies. Only later do they assemble themselves into chains. This preserves control over growth and organization. What makes giant siphonophores especially unsettling is that they blur boundaries people rely on. They're not modular machines. They're not swarms. They're not cooperative groups with independent members. They are single animals whose bodies are built from repeating lives. Evolution treats them as one unit. Selection favors arrangements that improve feeding, movement, and survival at the level of the whole. Individual zooids do not compete. They do not defect. They cannot leave. Their fate is shared completely. This shared fate allows complexity to scale in unusual ways. Instead of increasing brain size or muscle mass, siphonophores increase length, redundancy, and reach. Control emerges from structure rather than cognition. It is a different solution to being large. On land, large animals must coordinate limbs precisely to avoid collapse. In water, buoyancy removes that constraint. Distributed bodies can exist without skeletal support. Motion does not require symmetry. Giant siphonophores exploit this fully. They turn the ocean into a three-dimensional feeding field, occupying space rather than traversing it. Their presence is less about movement and more about coverage. Divers and submersible operators who encounter giant siphonophores often describe a moment of confusion. The animal does not register immediately as a single thing. Only as the camera pans does its scale become apparent. It feels architectural. And yet it responds. Tentacles retract. Lights flash. Swimming sections pulse. The animal adjusts without haste or panic. There is no rush in the deep ocean. Giant siphonophores demonstrate that intelligence and control do not always require a brain. They show that coordination can arise from repetition, proximity, and shared circulation. They are not systems pretending to be animals. They are animals that happen to be systems. In a sense, they embody an alternative path evolution could have taken more often but rarely did. Instead of building larger individuals, it built individuals that are built from individuals. That path is strange to human intuition, but it works. Giant siphonophores have persisted for millions of years, refining their architecture while other lineages rose and vanished. Their success is quiet, stretched across dark water, measured not in speed or strength, but in reach and endurance. They do not conquer space, they inhabit it. And in the vast, sparse ocean, that difference is everything. Across oceans, forests, rivers, and deep time itself, these animals all arrive at the same quiet conclusion. There is no single way to be strange. Some became strange by growing enormous, stretching bodies beyond what feels reasonable. Others became strange by shrinking, slowing down, or surrendering individuality entirely. Some solve survival by glowing in darkness, breathing air when water failed, or turning entire societies into a single body. Others did it by refusing to change at all, carrying designs that worked so well they endured mass extinctions without revision. What links them is not shock value or spectacle, it is honesty. Each animal reflects the conditions it faced and the problems it needed to solve. Scarcity shaped patience, darkness shaped light, isolation shaped cooperation, instability shaped endurance. None of these creatures are accidents or curiosities, they are outcomes. Together they show that evolution is not a ladder toward refinement or familiarity. It is a branching landscape filled with solutions that make sense only where they exist. What feels alien or unsettling from the outside often turns out to be precise, efficient, and deeply grounded in reality. Strangeness in nature is usually just adaptation viewed from the wrong place, and when you step back far enough, these animals stop feeling bizarre and start feeling inevitable. They are reminders that life does not aim to comfort intuition, it aims to persist. In doing so, it produces forms that stretch imagination, challenge definitions, and quietly expand what it means to be an animal at all.